It's really fun to see everybody coming in from all over the world. And hello, everyone. I'm very excited to the fifth annual Women in Microscopy Conference. I am Tirza Abbott, and I am the SEM Facility Manager here at the NUANCE Center at Northwestern University. I'm also a third-year PhD student in the Earth and Planetary Sciences Department. I'm going to throw it over to my co-host and founder, Stephanie.
I am Stephanie. I work at the National Center for Electron Microscopy, which is part of the Molecular Foundry at Lawrence Berkeley National Laboratory. And Tirza and I and the whole committee are so excited to have you here today. This is our fifth year, so we thought that maybe we'd start by telling you a little bit about how this all started. And this conference actually started from a conversation Tirza and I were having one day on the Fib. It was in 2021, in the middle of the pandemic and deep in a Chicago winter, and we were talking about how we could ever get to know other people in the field, and especially thinking about in our local Midwestern community. And this is how we came up with the idea for the conference. I don't know about you, but most of the ideas I have during a long day on the microscope are not the best ideas, but every now and again something sticks. And this was one of those rare occurrences. So Tirza and I set out to try and plan this conference, and we did it with a really fabulous planning committee, many of whom are still part of planning this event today. And we were just so overwhelmed and honored and surprised by the positive response we got. We had people come from all over the world, from all backgrounds, who were really excited in joining this community. I guess a lot has changed since 2021 and since the pandemic, but nonetheless, we've been hosting this event every year on International Women's Day as an opportunity to celebrate female identifying researchers in the field. And that's what we're going to do today. We've had keynote speakers, research talks, panelists from all kinds of different presenters, and all of these presentations have been just inspiring. It's also been really a pleasure to see this grow in other ways. We have, for example, been part of and heard about people meeting up online and in person at conferences and through collaborations and all kinds of other different ways. And we hope that today's event also spurs that kind of community.
Yes, is my audio a little bit better now? Okay, great. Yeah, so thank you, Stephanie. So it's hard to believe that it's our fifth year. It also seems like a really good time to be celebrating such a large milestone. It's important now more than ever for researchers across institutions to come together both on the technical and non-technical front, and we hope that our conference can help contribute towards these efforts. We also do want to recognize that there are other forms of diversity, and today's event speaks to a very small subset of these issues, but we hope it can lead to further conversations down the road. This event would not be possible without our fantastic collaborators, the Microscopy Society of America's Student Council and the NUANCE Center at Northwestern University. The Student Council is part of a larger microscopy society that hosts events mainly geared towards early career researchers throughout the year, including a pre-meeting congress at the big Microscopy and Microanalysis Conference in the summer. The NUANCE Center at Northwestern is a center of core facilities with complementary analytical instruments and characterization across the sciences and engineering. And both these groups have contributed tremendously to this conference, and it would not be possible to host it without them and the planning committee. We want to also take a moment to recognize the vendors that have contributed to this conference, and we'll be sharing more information about the Student Council, NUANCE, and our vendor sponsors during the break.
We have a very exciting lineup of speakers and panelists, which we're excited to share with you today, and we're going to start in just a minute. You'll get a chance to interact with the speakers through the chat throughout the conference, and we very much encourage you to ask questions and put your comments in the chat. We also have a lot to share today and want to be mindful both of timing and also leaving breaks for people to get a break from their screens. So if you do not get a chance to ask all your questions, we very much encourage you to do so after the event to follow up with us and the speakers and continue the discussion then. So I'll pass it back to Tirza now to introduce our keynote.
All right. Well, it is my great honor to introduce our keynote speaker, Dr. Michelle Thompson. Dr. Thompson is an associate professor of planetary science at Purdue University. Her academic journey started in Canada, where she earned 2 BS's degrees in geological engineering and biology from Queen's University. She then pursued her graduate studies at the University of Arizona, obtaining both a master's and PhD in planetary science. At Purdue, she leads a research group dedicated to understanding how planetary materials evolve after formation through the process of space weathering. Using advanced TEM techniques, she investigates samples from past and ongoing return missions, including Apollo, Hayabusa, Hayabusa 2, and OSIRIS-REx. In fact, in September of 2023, NASA's OSIRIS-REx project brought home pieces of the asteroid Bennu, and Dr. Thompson was one of the first 6 lead investigators on the scientific team and the first woman to study these samples. As an Earth and planetary scientist myself, I'm very familiar with her work, and I've had the pleasure of spending time at conferences and in the labs here at Northwestern with some of her students, and they've all been incredibly kind, fun, and welcoming, especially when I was a new member of the planetary science community, which is a testament to the collaborative and supportive environment that she fosters. I am truly excited to have her here with us today to share her expertise, so please join me in welcoming Dr. Michelle Thompson.
Well, thank you so much for that fabulous introduction. I'm just going to get my slides going here. All right, can everybody see that okay? Perfect.
Yes, we can.
Perfect. Well, thank you again to the organizers for this invitation. I'm so excited to be here, and it's so incredible to see the community that showed up today from all around the world. So I'm really excited about the opportunity to talk to you about some of the work I've been doing to study samples from all across the solar system. And when I talk to a group of microscopists, I usually start by telling them that I'm a material scientist, which is what I am. I just happen to study materials that come from other planetary bodies. And when I think about the kinds of questions that you can answer or ask when you're studying planetary materials, I separate them into 2 different categories. The first one is questions of origin. So what processes in the early solar system led to the diversity of planetary bodies that we see today? What was the chemistry and the environmental conditions that led to the evolution of asteroids and the terrestrial planets? The other category of questions that I consider are, how have those bodies evolved over the last 4.5 billion years of solar system history? And I myself study the second category of questions, trying to understand how these planetary bodies have evolved over 4.5 billion years. And to do that, I work on samples that have been brought back from these planetary surfaces. Now, many of you, or most of you, better be familiar with the moon. We brought back samples from the moon through the astronauts on the Apollo program in the 1960s and 70s, but you may be less familiar with other sample return collections that we have, including samples from asteroid Itokawa, and then samples that were recently returned from asteroids Ryugu and Bennu. So I'm interested in studying these materials using electron microscopy techniques to try and understand how they've evolved over the last 4.5 billion years. And one process that I'm particularly interested in studying is something called space weathering. So what is space weathering? Space weathering is a phenomenon that's occurring on the surfaces of airless bodies, and it causes the alteration of that surface material due to its exposure to interplanetary space. So here on Earth, we have an atmosphere that's protecting us from the harsh environment of interplanetary space. And in particular, there are 2 processes that are going on the moon and on asteroids that are driving changes in the upper few millimeters of soil grains on the surfaces of those bodies. The first one is hypervelocity dust impacts in the form of micrometeoroids. These are small dust particles that are hitting the surface of the moon or asteroids continuously. They are bringing a lot of energy, and so they're melting material, they're vaporizing material, and causing changes in the chemistry and the microstructure of the samples on the surface. And the second is the interaction of that surface material with energetic ions from the solar wind. The sun is putting out ions all the time in the solar wind, predominantly hydrogen and helium. These are being implanted into the rims of grains on the surfaces of these bodies, breaking down crystal structure. They're sputtering material from the surface. They're accumulating into vesicles or bubbles. And so all of these changes together alter the morphology, the mineralogy, and the microstructure of grains on the surfaces of airless bodies. So when we study samples that have been returned from the moon or from asteroids, we need to understand which characteristics are a result of their formation that happened 4.5 billion years ago, and which are a result of these space weathering processes that have been occurring over the history of the solar system. So now we know what space weathering is, but how did we even know this process was going on across the solar system? Well, we found out when we returned samples from the Apollo missions. And when scientists got these samples back in the lab, they wanted to first study them optically. So how does visible and near-infrared light reflect from the surfaces of the samples? When they did that, they compared two different sample sets. They looked at lunar soil, so just a scoop sample that the astronauts picked up on the surface of the moon, and compared their visible to near-infrared reflectance characteristics to a rock that they had picked up on the moon and then crushed up in the laboratory here on Earth to create an artificial soil. And they noticed there were three significant differences in the spectral characteristics between those samples. The first one was that lunar soils were much darker, meaning they had a lower overall reflectance. You can see that spectral line here compared to the ground-up lunar rock. They also had an attenuation of characteristic absorption bands. These absorption bands are really important to help us understand what minerals or what the composition of the surface is. And in the lunar soils, they were pretty much absent from these spectral features. And the third was reddening of the overall spectrum, meaning we get increasing reflectance with increasing wavelength for the soils compared to our ground-up lunar rock. So we knew some process was going on that was affecting this material exposed at the surface of the moon that was not affecting material inside of lunar rocks, that was not exposed to this interplanetary space environment. So that was our first clue that space weathering was happening on these bodies. Now we can see it in the reflectance characteristics of these samples, but we can also just see it with our eyes. This image here on the left is a lunar core sample that was collected from Apollo 17. Now that doesn't mean it's a sample from the core of the moon. What it means is that the astronauts took a metal tube and stuck it down below the surface of the moon to collect about 60 centimeters total of soil. And this material at the top was the material that was exposed at the surface of the moon, and you're going deeper into the lunar soil or regolith in this direction. You can see that all this material in this top layer is much darker compared to the material down below. That is the effect of these space weathering processes that are changing the reflectance and optical characteristics of the material. Okay, so now we know what it's doing to the reflectance characteristics. We can see the effects of space weathering just with our eyes. How do we recognize this process in the samples themselves? To do that, scientists went hunting for the microstructural and chemical characteristics in the soil grains themselves that were driving these changes in the optical and spectral characteristics. And I've got a few of these examples of what these features look like using electron microscopy data. First, we have the production of these grains called agglutinates. These are a result of those micrometeoroid hypervelocity impacts. You've got something coming in, it's melting material and welding together mineral fragments with this glassy impact glass as a result of those impact events. Now, this is just in the optical microscope. They started looking in the scanning electron microscope and the transmission electron microscope to see what features were going on at the nanoscale that could cause some of these changes in the optical characteristics. The first they noticed in this SEM image is this sort of hummocky or bumpy surface texture. These are vesicles that form below the surface as a result of those hydrogen and helium ions that are being implanted from the solar wind. If we take a cross-section of that grain and look at it in the transmission electron microscope, you can see these bubbles or vesicles that develop as a result of that irradiation from the solar wind. Now note the scale bar here. These are happening in the upper 100 to 200 nanometers of the surface of the sample. In grains where we do not have these vesicles, we do see the breakdown of crystal structure. Another TEM image with the surface of the grain here and moving into the interior in this direction. These fine scale parallel lines are lattice fringes resulting from crystalline material in the sample, but this outer rim is completely amorphous. That's because of that hydrogen and helium that's impacting the rim of the grain and breaking these bonds in the crystal structure. We also have more energetic particles that form bullet holes or tracks through the crystal structure of the grain. You can see them tracing them here in this transmission electron microscope image. Then we have impact events that are changing the chemical composition of the outer rims of the grains. They are melting and vaporizing material, and some materials lost from the system when you have one of those impact events, shown in this EDS map of this chemical rim on the surface of this grain returned from the moon. And then finally, we see the development of these melt and vapor deposits on the surfaces of grains. This droplet here is produced in an impact event. And if you look at these inclusions in this high angle annular dark field image in the TEM, these are nanophase iron-bearing particles that are produced in these impact events on the surface of these airless bodies. And these are our culprits. This is what's changing the optical and spectral characteristics of the material that we can observe in the laboratory. So there's a diverse set of characteristics, both microstructural and chemical, that are resulting from this process. And we need to be able to identify them in order to point towards space weathering as what's producing these features rather than them being characteristic of the inherent nature of the sample. So in order to do that, we need to use coordinated analytical techniques. We need to understand chemistry, microstructure, and the optical or spectral characteristics. So in my work, I use a lot of transmission electron microscopy, atom probe tomography. We study organic species with two-step laser desorption mass spectrometry, XPS, X-ray computed tomography, laboratory reflectance spectroscopy, and then of course, scanning electron microscopy. It really takes all of these tools to get a coordinated understanding of the samples. Today, I'm just going to talk about data from 3 of these techniques, which I thought would be of most interest to this group, including SEM, TEM, and XCT, or X-ray computed tomography. Okay, so now we know what space weathering is, we know how it manifests in these samples, and we know what tools we need to use in order to study it. So what am I trying to do with all of this? What I do is study the samples that are brought back from other planetary bodies to understand their evolution through this space weathering process. And today I'm going to talk about samples from one particular mission called the OSIRIS-REx mission. Now, this is NASA's first asteroid sample return mission. And with any good NASA mission, it has to be an acronym. So OSIRIS-REx stands for Origin, Spectral Interpretation, Resource Identification, Security, Regolith, Explorer. I will let you decide whether you think that is a good acronym or not, and there will be a pop quiz at the end of the talk. But this mission was really designed to go to an asteroid and bring samples back so that we could analyze them with these electron microscopy tools in the laboratory. This is what the spacecraft looks like, and you can see there's this arm that's sticking out of the spacecraft that was going to go down, touch the surface of the asteroid, collect that material, and then stow it in the sample return capsule and bring it back to Earth. This mission launched in 2016. It arrived at the asteroid in 2018 and then collected samples in 2020 and sent them on their way back to Earth, where they landed in 2023. Now, the asteroid that this mission was approaching was called asteroid Bennu. It's not just any asteroid. It is a carbonaceous asteroid, which means we expected to find organic molecules on the surface of the asteroid. And the reason why we want to bring samples back from asteroids is because on Earth, our Earth has evolved a lot since the beginning of the solar system. We have volcanoes, there's plate tectonics, we have a core, a mantle, and a crust. So if we want to understand what the building blocks of the early solar system were, we have to turn to asteroids. These are bodies that have not been significantly altered since their formation 4.5 billion years ago, other than through these space weathering processes. So going and getting samples from an asteroid, and particularly a carbonaceous asteroid that includes organic species, can tell us about what the building blocks of the solar system were and what the ingredients could be that led to the development of life early in Earth's history. So we sent our spacecraft off to asteroid Bennu, and before we sent the spacecraft, this is pretty much what we knew about the asteroid. We had a rough idea of its shape, we knew how big it was, and we had some idea of what its composition was. We knew that we expected to find organic molecules. It wasn't until the spacecraft arrived at the asteroid that asteroid Bennu really came into focus. Now, this asteroid is about 500 meters in diameter. And so if you see some of these big boulders that are sticking off the side of the asteroid, those are the size of 2-story houses. Okay, so this is really rough, rocky terrain. And the spacecraft spent about 2 years in orbit around the asteroid, mapping the surface, figuring out what the chemical composition was, and trying to identify a safe place that the spacecraft could go down to the surface, collect material, and safely stow it in the sample return capsule and bring it back to Earth. So this is that arm that was sticking out the surface of the OSIRIS-REx spacecraft, and there's a person in there for scale, so you can get an idea of how big the sample collection mechanism was. Now, this feature right here at the end, the circular, almost tubular feature, is the touch and go sample acquisition mechanism. So this is what actually collected material from the surface of Bennu and stowed itself away in the sample return capsule. So the next video I'm going to show you is the actual sampling event. So you'll see that circular tubular tag SAM feature that's going down to the surface of the asteroid, and you will definitely know when the sample collection event happens. So on the right, we have the view looking at the tag SAM approaching the surface of Bennu, and that is the moment of sample collection. I will say that in all of the models and all of the trials that we did for this event, it just looked like a really nice, gentle tap on the surface of the asteroid. When in reality, what happened was that we pretty much punched the asteroid in the face. And in the process, spewed out a lot of material from the surface of Bennu. Now, we were able to use the spacecraft to see if there was evidence for this space weathering process before and after the sampling event. So before this touch and go sample acquisition, we looked at the spectral characteristics of the surface and compared it to what it looked like afterwards. And we found that the spectral slope had changed, the overall reflectance or the brightness of the surface had changed, as well as the presence of those characteristic absorption features. So we knew that space weathering was operating on the surface of Bennu and that we could look for these characteristics in the sample when it had been returned to Earth. So confident that we had a space weathered sample in the sample return mechanism, you can see the tag SAM tucking itself into bed inside the sample return capsule for its long journey back to Earth, which took about just about under 2 years in order to send the sample return capsule back to Earth. The spacecraft approached Earth on September 24th of 2023. You can see the Earth over there as that kind of spherical object on the left-hand side. And that was the sample return capsule that got released from the spacecraft. You can see it flying down towards the Earth now. And the spacecraft kept on flying and is actually going out to study another asteroid. But the samples were safely on their way back to Earth's surface and landed at the Utah Test and Training Range on September of 2023. You can see the sample return capsule here with this nice parachute gliding them down to a gentle landing out in the Utah desert. These were recovered by the science team in coordination with the United States military. This is a military operation zone, and they were really helpful in helping locate and then bring the sample return capsule back. Here's the first image that we got of the sample return capsule on the ground. You can see the sample return capsule is charred. If you remember from that video showing the tag SAM tucking itself in, it was all white and gold, and it got cooked on its way in through Earth's atmosphere. So the sample return capsule was collected, it was brought temporarily to a staging area so they could check to make sure everything was as it should be, and then it was flown by military plane to NASA's Johnson Space Center in Houston. And we opened up the sample return capsule and got our first look at the material that we collected from asteroid Bennu. And this is what we saw. So the circular feature is the tag SAM. That has got where all of the bulk material from that really aggressive sample collection event was contained. However, what you might notice is that there's all this dust and dirt that's sitting on the outside of what we call the avionics deck. Here's a view kind of obliquely looking at that material. This is all particles from asteroid Bennu. What happened and what we had anticipated was going to happen was that the tag SAM was so full of material that it was wedged open. It wasn't actually completely closed. And so when the sample return capsule was coming in through Earth's atmosphere, shaking and tumbling, some of that material dislodged and came out of the tag SAM and ended up on the avionics deck. Now you may think, oh no, this is a big problem. Actually, this was great. We anticipated this might happen, and that enabled us to get access to sample a lot quicker than the several weeks it took to get into the tag SAM and disassemble all the bolts and unscrew everything and take off the witness plates and do all of that really intense disassembly of the tag SAM. Instead, Curation was able to scoop up a little of this material and hand it out to the science team so that we could get started on our analyses right away. Eventually, when we got into the tag SAM, it showed us that we'd returned over 121 grams of material from asteroid Bennu. We had been hoping for at least 60, so we more than doubled the amount of material that we brought back. And that makes it the largest asteroid sample return mission in history. There have been 3 overall. This is NASA's first and makes it the largest of any of the missions that have brought back material. You might notice all the material looks pretty dark, almost like what you might pull out from your barbecue, your charcoal barbecue. But this was really exciting to know we had brought back all of this material. Now, I was very fortunate to be a part of the Tiger team, which was a group of scientists that was assembled almost like the Avengers in order to do the first 72 hours of sample analysis. They scooped up some of that material from the avionics deck, delivered it to us, and we had 3 days to do as much microscopy on the samples as we possibly could so that we could understand what its composition was, what its microstructure was, to report out to the press, to report to NASA, but also to tell the rest of the science team what the sample looked like. So that could help them guide what materials they wanted to request and what samples they wanted to analyze. So this is me looking extremely excited, holding the first vial of material from asteroid Bennu. I was the first woman that got to work on these samples, which was just the most incredible opportunity, but I was a part of this brilliant team. And here's your first look at Bennu material, just in a dimpled glass slide as we were looking at it under the optical microscope. The first thing we wanted to do was say, okay, how can we non-destructively analyze the sample to see what it looks like on the inside? So in order to do that, we performed X-ray computed tomography, and this is a 3D scan of one of those Bennu particles that was completed about 12 hours after we got our hands on the first sample. You see there are differences in contrast. That's a result of different chemical composition of those phases. We could also look at the surface morphology of the sample to understand if we could identify any evidence for these space weathering processes on the surface. We're able to pick out the distribution of these high density mineral phases. That gives us an idea of what the bulk mineralogy is and how much of these particular components we had in the sample. So once we looked at the sample in 3D, we wanted to get it into the electron microscope and search for evidence of exposure on the surface of asteroid Bennu. So we started looking at the sample in the scanning electron microscope, and we found our first evidence for surface exposure in the form of microcraters. These are craters that form as a result of those micrometeorite impacts, those hypervelocity dust particles that are hitting the surface. So you can see this almost like a hole punched in the surface of this grain from Bennu. There are all these fractures that are running out from the crater. And then if you look at higher magnification, there's this really vesiculated, frothy, almost deposit that's lining the inside of this crater. That is the melt deposit that formed as a result of that high velocity impact or melting material on the surface of Bennu. Now, it wasn't enough for us just to say, okay, great, we've seen evidence for space weathering on the surface of the sample. We wanted to know what this crater looked like in cross-section. So we extracted a fib section, so now a cross-section of that crater. So you're looking at the surface of the sample here, and you're going into the grain interior in this direction. And we could trace the track of that impactor throughout the grain from asteroid Bennu. Now, this thing penetrated over 70 microns from the surface of the sample, and it was going either fast enough or was strong enough to penetrate this really high density phase, which is an iron sulfide material, basically an iron plate that's sitting in the sample. And this hypervelocity dust impactor penetrated right through that plate, didn't even slow down, and went 70 microns deeper inside the sample. So these kinds of analyses can tell us information about what the population of impactors looks like, where in the solar system are they coming from, what kind of composition must they have had in order to penetrate this deeply into the sample, and gives us a clue about the environment at the surface of asteroid Bennu. Now, we found beautiful large microcraters, but there are some grains that had a huge distribution of microcraters across their surface, not just one big impact crater with all these radial fractures, but instead 1 to 2 micron craters that are spread all across the surface. So this is one of those grains from asteroid Bennu, and each of these yellow squares represents the location of one of these small impact craters. They've got these raised rims, as you can see in the scanning electron microscope images. Some of them has this vesiculated melt that's glassy amorphous material lining the crater. But the great thing about being able to identify these impact craters is that we know what the dust flux is in this part of the solar system. We understand how many impacts you might expect over one particular surface area. And so by counting them distributed across the surface of the grain, we can actually understand exactly, a range of how long this grain sat exposed at the surface of the asteroid. That tells us things about the dynamics on the surface of the asteroid. How often are they being resurfaced? How often are larger impacts, generating new material? Is the surface being disturbed by interactions with, other planets across the solar system? So by analyzing the distribution of these microcraters, we calculated that this grain had sat at the surface of asteroid Bennu for between 20,000 to 80,000 years. Now, we wanted to see how these microcraters compared in cross-section to the microcraters, to that one large microcrater I showed you first. So here are a TEM cross-section of 2 of those different microcraters. They're typically less than, 5 microns in diameter as well as in depth. This is the cross section. So you're looking at the surface of the grain here, and you're going into the grain interiors, you move down. All of this fluffy, hairy looking kind of material, these are phyllosilicate minerals that we see returned in the samples from asteroid Bennu. These include water as a part of their crystal structure. So by studying the composition and distribution of these minerals, it can tell us about how much water there was present in the early solar system and available for asteroid Bennu. We can also look at these little Dalmatian spots, or these nanoparticles that form at the base of this microcrater, to try and understand what their composition is, what their mineralogy is, because that impacts how the optical or spectral characteristics of the surface are altered through the space weathering process. And then we can compare these microcraters one to the other to see how the size, how the diameter to depth ratio changes. All of that can tell us about the population of impactors that the surface of Bennu and grains in the soil were experiencing. In addition to our microcraters, we can also see evidence of those micrometeorite impacts in the form of melt splashes. If you think about impacting the surface, it's melting material in the crater, but it's also ejecting melt material that can then be distributed across the surface of the grain as well. So in addition to the craters, we see melt droplets or glassy splashes all across the surface of these particles, some of them more than 180 melt deposits spread across the surface. And looking in the scanning electron microscope, the morphology and composition of these melts is really interesting. Some of them have this almost droplet-like shape. Some of them are really almost like amoeboid shaped, but all of them have vesicles or bubbles that are distributed throughout the melt deposits, as well as these higher Z-phase nanoparticles, that include the iron nanoparticles like we've seen in samples returned from other planetary bodies. The size of these nanoparticles varies. Some of them are, a few nanometers in diameter, moving all the way out to approaching a micron. And so we wanted to understand exactly what their composition was, what their distribution was, in order to understand what influence they might have on the spectral or optical characteristics of the sample. So to do that, we can take Fib cross sections to look at these melt deposits in the transmission electron microscope. This is an example of one of those transects that we looked at in the TEM. So now you're looking at the surface of the sample here and going into the grain interior in this direction. And this amorphous material at the surface, this is all the melt deposit. All of these bright areas are vesicles that are formed through outgassing of volatile species like the water that we see in these hydrated mineral phases in the sample itself. We also see these these dark Dalmatian spots or nanoparticles that are distributed throughout the melt itself. And we can see that those nanoparticles are enriched in iron, as well as in some maps, we've got nickel as well as sulfur. This is interesting because most of the nanoparticles we see in samples from the moon are just iron metal. And here we have nickel and sulfur playing a role, which is going to influence how they affect those spectral or optical characteristics that we can observe for asteroid Bennu. Some of the melt deposits also have these whiskers that are enriched in iron or nickel that you can see in this SEM images here that are protruding or sticking out from the surface of those melt deposits. We can take cross sections and look at these features in the transmission electron microscope as well. And you can see those in the cross section here, almost like hands reaching up from the interior of these grains, telling you that they've been affected by space weathering. And looking with EDS mapping, we can tell that the composition is enriched in nickel and iron and formed from likely iron-nickel metal. The origin for these whiskers is still a little unknown. We think that they might be forming as a result of kind of this compressional stress that forms when you have a micrometeorite impact, compressing the surface of the sample, and then it squeezes this material out from the melt deposit and forms these little whiskers or fingers that are sticking out from the surface. Now, I've talked a lot about evidence for that micrometeorite impacts, but we can also look for evidence of solar wind irradiation, that hydrogen and helium ions that are being implanted into the samples. And when we look for features related to solar wind, we focused on these small bubbles or vesicles that are right at the intersection between this overlying melt deposit and all of the regular material in the sample itself. We could use secondary electron imaging in the TEM in order to see in the Fib section which of these vesicles have been perforated and which vesicles are actually still intact, so that we could try and identify the hydrogen and helium directly in the sample to prove that they were containing species from the solar wind. So in order to do that, we performed electron energy loss spectroscopy, or EELS, in the TEM. And in the low loss energy regime, we can actually analyze the samples for helium directly. It's got a peak on the plasmon at about 22 EV. And when we perform these EELS analyses of those vesicles at the interface between the melt and the underlying material, we see evidence for helium derived from the solar wind, telling us that even before this micrometeorite impact deposited this melt on the surface, this grain was exposed to solar wind irradiation on the surface of Bennu. And this was the first detection of solar wind species in the samples from the asteroid. And then finally, we have those bullet tracks, those higher energy particles that are coming off the solar wind and leaving these trails of ionization damage that we can observe in the TEM. Just like we can do for the micrometeorite craters, we can count the density of these tracks, and we know what the flux is for these tracks in the vicinity of where asteroid Bennu is in the solar system, and that can give us an exposure age. So when we count the density of these tracks, it tells us that this grain was sitting at the surface of Bennu for about 45,000 years. Now, this is right in line with the estimates that we have from our micrometeorite impact density between 20 and 85,000, and tells us that grains are sitting on the surface of the asteroid for tens of thousands of years before being disturbed or buried deeper in the regolith. So what does all of this data that I've just overwhelmed you with tell us? Well, this is our first asteroid sample return mission that NASA successfully brought back material from Bennu. Our first look at asteroid Bennu samples told us that they record their exposure to interplanetary space. We see evidence for micrometeorite impacts in the form of melt deposits, in the form of microcraters, these nanoparticles that are forming distributed throughout the melt. And we also see evidence for solar wind irradiation. We've detected helium in the samples, in those vesicles produced by solar wind irradiation. And we see evidence for those energetic particles from solar flares that tell us about exposure timescale on the surface as well. And we need a really diverse set of microanalytical tools. We talked about XCT and TEM and SEM, but within those techniques, we've used energy dispersive X-ray spectroscopy, we used electron energy loss spectroscopy, we used backscatter, secondary electron imaging, and all kinds of TEM imaging as well. So we need these diverse tools and techniques to be able to characterize the samples effectively. We know grains sat at the surface for tens of thousands of years, and that tells us about how the dynamics on the surface of asteroid Bennu are operating, how often the material is refreshed. But really, this is only just the beginning. Our first round of the samples have been back on Earth for about a year, I guess a little closer to a year and a half now. But the purpose of bringing samples back from another planetary body is about creating a legacy. I'm working on these samples, but they're going to be available for the next 100 years. So hopefully some of the people that are participating in this Women in Microscopy event are inspired to, look at these samples, and you'll be leading the charge in our understanding of space weathering and planetary materials in the future. With that, I just want to say thank you and end with my favorite quote, which I think kind of encapsulates my entire career, which is that where the telescope ends, the microscope begins. Which of the two has the grander view? I feel like I am privileged to be able to look at it on both sides, And I want to say thank you to the team, the entire team for OSIRIS-REx, as well as the curation at NASA that provided us with these incredible samples, and my wonderful students and postdocs in my research group, because without them, none of this would have been possible. And with that, I am more than happy to take some questions about returning samples from asteroid Bennu. Thank you.
Thank you so much, Dr. Thompson, for sharing that with us. It was extremely fascinating for myself, but there were also just a number of questions that came in through the chat. So I would like to read off a few, and if any of the, I'll read off the few. And if anybody has any additional questions after the fact, please feel free to use the raise hand feature and we'll get to you. So one of the first questions was from Miranda Lynch and I believe Ellen Lavoie. There was a question on, was there a risk of contamination of the materials from the deck region that you collected from the spacecraft from the asteroid to Earth? And were there any problems from the re-entry process, and how could that impact what it is that you are seeing, especially since you collected the samples straight from the deck and then did the analysis in 3 days? What could that tell you, and how did it change from the material that was collected inside?
Absolutely great question. So once the sample return capsule made its way to NASA Johnson Space Center, everything was disassembled inside a glove box, so under dry nitrogen. So there's no exposure to Earth's atmosphere. So we weren't worried about any contamination from Earth. However, it's a very good question about, this material was not kept inside the tag SAM. Was there other material just in the sample return capsule? And that was something we were very cautious of. One thing I didn't talk about today, but there were some unexpected mineralogy phases that we found in the sample that for the first couple of days, we were not sure if they were actually from the asteroid or if they were as a part of contamination. Now, we had done all of our due diligence. We had a library of all of the material that was used in the fabrication of the spacecraft. There were very strict protocols on what they could use and what they couldn't, and there was really limited amounts of material that could overlap with what we expected to see in the samples. But it was a consideration, and we had witness plates, we had all kinds of test materials to be able to validate and verify that what we got was actually from the asteroid. Now, I will say, All of this has now been validated with the samples that were brought out of the actual tag SAM. But in those first 3 days, I could not have given this talk and said, look, here's all these things. We presented everything with, we think, but here are other options. And so it's important to also know what the limits are, even using these incredible techniques in the electron microscope, to be able to understand provenance. Is this really from the material, or is this, as a result of the spacecraft? But we've had them for 1.5 years now, and we know we got it right. So, but great questions.
That's awesome. I think, yeah, just even knowing that there is a protocol to kind of validate the materials beforehand, so that way you can differentiate between what it is that is brought back versus what you've had.
Yeah. We
That's
had a whole contamination control working group whose entire job was just making sure that the samples, that we knew what could possibly contaminate the sample. So they were very important in those first 3 days.
I can imagine, yes. The next question that we have is, what is the size of those impact grains, and did they vary? Did they vary across like different regions that were collected? And yeah, they just said, they also commented, it's incredible to see how much a piece of dust can cause damage.
Yes.
It was very interesting. That micrograph was beautiful.
Oh, I have to shout out my graduate student, Lizette Melendez, who might actually be on the call. She was with me on the SEM when we found that impact crater. So, we were pretty excited about that. The size of the particles can vary, but we're thinking in the sub 10 micron region are the size of these things. And, the velocities vary around 1 AU, meaning where we are in the solar system. They can be anywhere from 5 kilometers per second to 25 kilometers per second. So these things are really moving. And that's how they're able to melt stuff, vaporize stuff, and some of them leave that huge trail of damage. Now, the material that the Bennu material is generally very, very soft. It's not other than that kind of metal plate I showed you, it's not a very robust, hard material. And so some of these can be moving slower and still go a lot deeper. The 1 to 2 kind of micron size particles, those are, or impact craters, those are probably created by, micron sized dust particles that are hitting the surface. But it is surprising. You would be shocked by how much damage we can get from just small particles hitting the surface.
Yes, they might be small, but they're moving at very fast speeds.
Small but mighty. Absolutely.
Yes. The next question that we have is, what form of water is present within, because you did mention that there was some water identified within the micrographs that you had presented. So what form, and then how did you identify that it was actually water in the grain from the STEM image, or maybe it was a different type of technique?
Yeah, so we use several different techniques to actually identify the water, including some of that reflectance spectroscopy that I showed you. There are water features or absorption characteristics. We know that there's water because we can identify the mineralogy based on just the lattice fringes from those TEM images. The water is usually in the OH form, and it's a part of the crystal structure. It kind of hides in these interlayer spacings between the different crystal layers in those minerals. And these are minerals that we have on Earth too, these phyllosilicate minerals. So you can think of clay, if you ever heard clay minerals. We have them here on Earth, but being able to identify them and see what their abundance was in these materials can give us a clue about kind of what the volatile or water budget is like for asteroids that formed in early solar system.
Oh my gosh, that's so cool. Just to even think that you can, deconstruct that. I mean, because you said they sit in the middle of like the lattice, the crystal structure. That's really cool. We have about 2 minutes, I think, until the end, but we can go ahead and try to answer maybe 1 to 2 more questions. So the next one that I have was, what carbonaceous compounds were found in the asteroid dust, and is the composition homogeneous?
Great question. So preface this with, I'm not an organic chemist, so apologies if I butcher this, but all kinds of organics. I know they have found amino acids, all the essential amino acids that we have for life here on Earth. They found the ingredients for nucleobases. They have found all kinds of stuff. That's all I'm going to say right now. But there's a paper, because I don't want to say anything wrong, but there is a paper that just came out in the journal Nature Astronomy, which talks all about the organic composition. And it's definitely heterogeneous from piece to piece. It's not necessarily evenly distributed throughout, but it's one of our sample return collections that has the most organic carbon that we have seen in our sample collections. And it's very exciting because there's other minerals that point towards an environment that might be hospitable to these kinds of prebiotic chemistry that might be going on even in the early Earth. And so even though we didn't find life in the samples, we kind of found the ingredients for life, and we might have had the environment where life, could have been hospitable. So very exciting for the organic chemistry team.
Wow, that is super fascinating. I'm going to look up and see if I can link that paper here. There are 2 more questions, but we are at time. So just to keep everything running, I will also just reiterate those questions. So maybe if you're in the chat, you can answer them. And yeah, so I will pass it off to, thank you so much, Dr. Thompson. That was extremely fascinating.
Great, thanks everyone. And I'll answer some questions in the chat.
Awesome, thank you.
Welcome back, everyone. We're going to get started with the research talks in just a minute here, so please join the breakout room. And if you have any trouble joining or have any questions, feel free to put that in the chat.
Trinity College Dublin, and I'm working on developing low-cost, high-speed electron detectors for 40 STEM measurements. So as you might be are familiar with 40 STEM. 40 STEM is an electron beam technique which uses electron beam to scan across a sample. But when we consider this technique to a conventional STEM, 40 STEM is different, which collects not only the images, but also collect the diffraction patterns. And it is helpful for the spatial and angular informations. And applications of this 40 STEM, such as DPC technologies or some other tychography or orientation mapping, etc., which is helpful in the biological fields, material science field, make this technique most important in the electron microscope world. And let me take you to the history of these detectors. So if you compare the detectors with a camera, I think most of you are familiar with the cameras used like with film-based cameras, CCD-based cameras, which we are using in the mobiles. And if you compare with the cameras with the detectors of TEM, the TEM cameras were also using photographic films in the past, and then they moved to CCD-based cameras, and then now we are doing direct electron detections. So the 40 cameras which are existing now is highly efficient, and it is also giving us high resolution, high signal to noise ratios. So why should I replace these cameras? So the main problem is the cost. The cost of the 40 STEM detectors are increasing to about 10 million. And as you can see, the Carmen BSE, which is a backscattered secondary electron detectors, which is a scintillator-based detector, and it is the most cheapest detector available, where when you compare it with the existing pixelated 40 stem cameras, the prices are increasing. So how can I achieve the low-cost detector? So the plan is to advocate a standardized open flange specifications. So if you are not familiar with a flange is a vacuum sealing, a metallic sealing, which is used to achieve vacuum conditions. So we are advocating standardized open flanges, which is based on conflat standards. So the TM camera designs can be made on these conflat standard designs, and you can use this or interchange these cameras or the whole detector setup between different instruments between different institutions, and you don't have to make a new design, and you can just reuse it and interchange, and can reduce the financial barrier and of even the hardware developments, and it can enhance the sustainability. On the right hand side, you can see the designs which we have already made for different instruments, which is JOL, Titan, which is a thermoofficial cameras, and for the Gethan cameras. So these are based on the CF63 and CF35 flanges. And to prototype these flanges, we have already started comparing the column sizes of the instruments which is available in the Trinity labs, which is JOL and thermoofficial Titan. We have compared the column sizes and the flange. We have made a round flange design for the JOL and a rectangular flange design for the Titan. And we have also used 3D printing to 3D print these designs, which with the 3D printer available in the labs. And once we finalized the designs, we made this into machining. We machined the 3D flanges in stainless steel. And next part is testing, the most important part, where we have to make sure the vacuum condition is safe enough with these flanges. So what we have done is we have tested our machined flanges on the JOL microscopes, and it is safe enough to go. So as I have talked about the low cost, I'm also introducing a new insertion and retraction setup, where you can use this setup to, if you have to use EELS spectroscopy, or if you have to do other detections while you are using the stem, you can insert and retract the Hall detector setup with a bellows or a full nipple designs on this CF standard flanges. And along with the low cost, we have to also consider high speed detections. So how can I achieve that? So as I mentioned, I will be using a scintillator-based detectors. So for a scintillator-based detectors, I have to choose a best efficient scintillator, and I have to also use a silicon photomultiplier for the detection part, and also a PCB design. So the choice of a scintillator is the most important thing. So YAG is the current used scintillators in the TEM studies. And I have also considered other scintillators like LISO, YAP, BGO, YSO, and LSO. Why? Because of the wavelength, decay time, and the photo yield. So these three parameters, wavelength, decay time, and photo yield, are the most important things I should consider to make sure that these scintillators are best for the higher speed and higher signal to noise ratio and higher number of the detection of electrons or photons. So how can I make sure these scintillators are good enough? So I have to also consider a silicon photomultiplier, which will be compatible to these scintillators. So the wavelength of these scintillators should match the wavelength of the emission peaks of the silicon photomultipliers I'm using. And pulse detection technique is another pulse counting technique is a technique where I can detect the individual electron events at a detector. So what I have done is testing these before going directly to the TEM. I have tested these scintillators on the SEM Fest to make sure that scintillators are best. So I have tested YAG Fest on the silicon photomultiplier on the size Evo SEM, and we have got a pulse where you can see we are getting some single events or single photons events. So why these pulses are important? So the pulses can help me to analyze the rise time and decay time of the scintillators. So these rise time and decay time can give me an information about how fast is the detection happening on a scintillator. So currently we are trying to make the testing of different scintillators that I have chosen. The 6 crystals should go on the SEM Fest, and I should get an information about the rise time and decay time. So I can make sure how quick the detection is happening with these scintillators. So in the future, that's the plan. The plan is test these scintillators on the SEM Fest and then check the rise time, decay time, and find an efficient scintillator material, then make a PCB design which will be good enough to go on the TEM. It should be like compact design, I cannot use the SEM design for the TEM. So I have to make a new PCB design and then test it on the TEM JOL Fest. Thank you. And I would like to thank my supervisors and all other group members who have helped me a lot in this project. Thank you.
Amy is a PhD student from Stanford. So whenever you're ready, Amy, go ahead and share your slides and get started. If you could unmute yourself.
Yep, thank you.
Back in the Zoom world.
Yep, back in the Zoom world. Thank you so much for the kind introduction. Can everybody see the slides? Awesome, okay. Yeah, it's my pleasure to be here today to talk about my work as a member of Jennifer Dionne's group at Stanford University and our work revealing structural and optical changes of ammonia catalysts under realistic reactor conditions using in situ electron microscopy and electron spectroscopy. So, primary chemical production, we're talking about chemicals like ethylene, methanol, ammonia, contribute over 9,000 metric tons of CO2 per year. Part of why these chemical processes produce so much CO2 is that they require very extreme reaction conditions. So for ammonia synthesis, as an example, we're talking about temperatures ranging from 400 to 500 degrees Celsius and pressures of upwards 200 bar. So that's 200 times ambient atmospheric pressure that we're all feeling right now. Luckily, photocatalysis, specifically plasmonic photocatalysis, introduces new mechanistic pathways that can allow these same chemical reactions to occur under ambient pressures, so thereby reducing the amount of CO2 we're emitting. My work focuses on ammonia synthesis. So I study gold ruthenium solid solution catalysts that have been demonstrated at the reactor scale to produce ammonia under light illumination. However, we throw all these things into a reactor and we don't actually know how the catalysts are transforming or changing their stability during chemical synthesis. Enter in TEM. We use a nanoreactor inside of a TEM through a custom-built holder that allows us to flow gas mixtures in and out with different flow rates at near atmospheric pressures. We can actually go slightly above atmosphere. Temperatures of upwards of 1,000 degrees Celsius, and using fiber optic cable, we can actually couple in light and shine light on our sample. So pretty much do photocatalysis in the TEM. However, in situ microscopy is notoriously complex, and so we want to make sure that we're understanding how the system responds to each of these stimuli independently. So for the sake of time, I think I'll talk about how the systems respond with heat and gas for this talk. We'll save light for another day. So to do heating, our heating work started off in vacuum, where we ramped the system from 0 to 750 degrees C, taking snapshots at these intermediate temperatures. So to kick it off with a data set, this is 5 example gold ruthenium particles that are polycrystalline and homogeneous, which means the gold and ruthenium are nicely intermixed. This may or may not be foreshadowing. As we increase the temperature, we see that the particles remain pretty much unchanged until we start getting to temperatures around 600 degrees C, where we see this formation of this light contrast region. we were a little bit like, are the particles melting? What is happening here? And just to zoom in on some lattice, we can see that these different contrast regions are definitely within the particle. They're not growths on top. Luckily, X-ray energy dispersive spectroscopy answered our question and revealed that these lighter contrast regions were actually ruthenium-rich regions, and that the particles had undergone a phase segregation or a separation of our gold and ruthenium phases. High-resolution STEM HADF actually helped us figure out that this ruthenium takes on a new phase. So when they're in a solid solution, we have typically FCC crystals, but post-segregation, RU actually takes on an HCP crystal structure. So we're doing photocatalysis. So our first question was, how is this structural change impacting the optical responses of our crystals? So we had to answer this using monochromated low-loss eels. So we actually observed the plasmon of these catalysts, which is around 2.5 eV, and watched its evolution during phase segregation. To do this, we took line scans of each particle and then averaged it to have a surfaced average response, which is then plotted here on the right. And so we noticed some pretty cool things, which I guess first is as we heat the particles, we see a broadening and a redshifting of the plasmon, which is expected. But kind of unexpected was that post-heating, if we compare so the purple, which is room temperature after heating, so they're phase segregated, with the gray when they're a solid solution, we actually see a narrowing of our plasmon peak and even a slight blue shift, showing that we almost have a stronger optical response post segregation. So this is exciting. If we want to do photocatalysis, we really want it to be able to couple well to light. So our next question, basically we see this for a lot of different particles. Our next question was, how does gas change these morphological and optical responses? So to nerd out a little bit, these experiments are notoriously difficult, and part of it is because we're dealing with huge pressure gradients. If you think about the pressure inside of a TEM column, we're talking roughly 10 to the minus 7 millibar, and we're working with pressures on the order of 1,000 millibar. So our tiny 50 nanometer silicon nitride windows are separating a differential of 10 orders of magnitude. So these experiments are not for the faint of heart, but they are rewarding. So when we heat our particles in the presence of gas, we see some new and exciting things. First, we do see the same phase segregation, but it occurs at slightly lower temperatures. And then in terms of faceting, we actually see, instead of a slight rounding that we normally see when heating in vacuum, we almost see a sharpening or a strengthening of the faceting, which is likely due to the gas altering surface energies. And then lastly, we observed this very interesting formation of a pseudo core, which we initially expected would be maybe a ruthenium gold core shell. But again, EDS to the rescue actually informed us that we think it is a void. So either through like a Kirkendall diffusion or through a gas-mediated dealloying, the core or a good chunk of this particle is actually being removed in the presence of gas. So this has some broad implications for how these are going to behave as catalysts. We observe a variety of morphologies. They are not all this kind of void formation, but all have this hexagonal morphology. So we're excited to study definitely the optical responses of this going forward, because the sharpening of the facets will change the plasmonic response, as well as the surface area for catalytic chemistry. So with that, to summarize, we first do in vacuum in situ heating to observe this gold ruthenium phase segregation confirmed by EDS. We use monochromated low-loss eels to observe the changes in optical response of these catalysts during this phase segregation and observe an actually stronger plasmon post-separation. We finally add in gas to achieve more realistic catalysis conditions and see changes and tuning of the faceting and even internal structure of the catalysts. With that, I would like to thank my advisor, Professor Jen Dione, Dr. Peri Muradafar. She's been with me through like all of these experiments. I can't do it without her, as well as the rest of the members of my group, our TEM support staff here at Stanford. They are amazing. And then funding sources. Great. And with that, I'm happy to take questions if we have time.
Thanks so much, Amy. Doesn't look like we have any questions in the chat, so I'll just ask my own question. Oh, we have a raised hand. Emma, go ahead and unmute yourself and ask your question.
Hi, Amy, awesome to see your work. I met you at GRC this past summer, and I saw a little bit of this on your poster. I'm curious if you can give us a little bit of a some foresight on how it's been going with the light experiments. Have you seen any changes in how your structure of your catalyst is changing under inoperando conditions compared to your photocatalyst?
Yeah, for sure. So we've done, I think, 2 or 3 successful light experiments. It's quite something to have heat, light, and gas all going at once. And preliminary results are that we actually may see that the segregation is favored to optical hotspots. So if there's any pre-facening of the particle, we start seeing subtle phase segregation along where those plasmonic hotspots may be. But there's definitely much more work to do. And this was exciting with like a 450 nanometer light. So it was in the interband regime for gold. So excited to see what happens when we can do more of a wavelength sweep.
Awesome. Thank you. Can't wait to see the evolution of that work.
Yeah, me too.
Yeah, thanks so much. One more question here that we have time for. One person asked, how can the gas insertion change the surface energy and promote faceting? And what's the underlying reactions? We have about 1 minute here.
Okay. That's definitely a complex question. My understanding is that hydrogen can reduce species. So when these are colloidally synthesized nanoparticles. So when you have hydrogen, which is one of the precursors that is for ammonia, so these are all done in a mixture of hydrogen and nitrogen gas, you can get reduction of species. And so at higher temperatures, I think that allows for different rates of diffusion, and thus some of these materials can be carried away by the gas preferentially. So I think it's likely that ruthenium is being carried away through this gas flow at high temperatures, like 750 degrees C.
Great. Thank you again, Amy. Keep bringing the questions in the chat. The speakers can respond to those as we go. Next up, we'll have Madeline Meier, who is a postdoctoral fellow at Northwestern. So Madeline, go ahead and share your screen and begin whenever you're ready.
I thank you all. Are you able to see my slides?
Yes, looks great.
Okay, great. Thank you for that introduction, and thank you all for being here today. I'm excited to share with you all some recent advances and challenges in the field of cultural heritage science that we've been working on at the Center for Scientific Arts here at Northwestern University. So the Center for Scientific Arts is a partnership between the Art Institute of Chicago and Northwestern University. The goal of the center is to combine a top-tier research institution with a world-renowned museum to advance research, education, and outreach at the intersection of science, engineering, and the visual arts. In addition to collaborations at the Art Institute, we have partnerships with museums and institutions all over the world. All fields have specific obstacles to overcome and setbacks and challenges when facing research. We talked today about the keynote about degradation in space, which was so fascinating. But cultural heritage also has some really unique characteristics that make research very challenging at times, but ultimately that much more rewarding. Some of those highlighted here are the variability of materials. The objects studied in cultural heritage span a wide range of material classes, and each object can also have a lot of variation within its object itself. Shown here are just a few examples of the different types of objects we can study: ancient textiles, paintings, feathered objects with metal components, as well as more modern plastic materials. Sampling is also a huge issue within the field because of these objects are often artifacts, and we're trying to do as much non-invasive or contactless analysis as possible. And if and when we are able to get samples, the size of those samples can be very limited. Finally, degradation. The objects and samples associated with these are often hundreds, if not thousands of years old, so they have undergone some degradation over time. Additionally, the conditions that objects are in, temperature, humidity, can also vary and have different effects on how the material has evolved during this time. And in each of these projects coming up, I want to highlight some of these challenges and highlight the methods and analytical techniques we've been using to address them. The first project here is a collaboration with the Field Museum of Natural History in Chicago, investigating a series of calendar screen panels from the Qing Dynasty. The goal was to identify and better understand the materials used in constructing the panels, and specifically the fabrication technique known as chongchui. The specific craft here demonstrated, known as chongchui that I just mentioned, is also known as dotting with kingfisher feathers. And so while these beautiful regions of specifically the blue on the calendar screen panels present as a continuous medium, It's actually individual pieces of feathers that are meticulously glued to the surface that are responsible for this visual appearance. This series of panels was of great interest to us, in part because of its size, as most examples of changchui consist of smaller hairpins and jewelry, but also because of the combined usage of structurally and pigmentary-based colorants, as highlighted by the top for structural and the bottom micrograph insects, respectively. Structurally based colorants can be found throughout cultural heritage, although less common than dyes and pigments, but have been historically understudied because of challenges related to differing mechanisms of coloration and angular variability in structural coloring that, when combined with the three-dimensional nature of these objects, makes for a very complex research process. To address this and better understand the mechanism of kingfisher coloring, we first aim to identify the mesostructures responsible for the coloration using purchased reference feather samples, as sampling was not possible. On the left is the image of the common kingfisher, historically the most frequently used species in the craft. The right are scanning electron micrographs of a reference kingfisher feather. Through the SEM analysis, we were able to discover the structure responsible for the bright blue coloring is a sort of a semi-ordered array with this almost nano-sponge-like appearance. The structure's features of the pores are on the orders of hundreds of nanometers, and the spacing between adjacent pores is on the order of 200 nanometers. To better visualize the angular-based changes in coloring, we turn to optical scatterometry. Optical scatterometry or optical goniometry measures the reflectance spectra of a sample over a range of angular values. As depicted in this schematic here, the detector moves in sort of an arc-like pattern, collecting reflectance spectra with a degree of 1 degree resolution, or sometimes even finer. Doing these measurements on reference kingfisher samples, this color chart depicted here visualized the observed color of the feather in the blue region as a function of angle, so the different hues and variations of the color you would see if you would tilt the sample. To do this and achieve this sort of visual representation, we took the spectra from the optical scatterometry and converted it to RGB color space and plotted it at the corresponding angle. We're currently working with Argonne National Lab to understand and examine these nanostructure features even further, and are really excited about the work in this project. So in the Kingfisher project, sampling was unavailable, but even when sampling is possible, in the case of our work on ancient Egyptian textiles, the degradation and the size of the samples, on the order of hundreds of micrograms in this case, can present a lot of challenges. The Art Institute of Chicago has a large collection of ancient Egyptian textiles, with the date of these textiles ranging from 1st century BC to 13th century AD. In this project, over 40 textiles were examined via a combination of non-invasive and microdestructive techniques to identify dyes present in the sample. SEM can provide insight into fibers present in textile samples as exhibited by the micrograph here, with the representative cuticle or scale features commonly seen in wool fibers. In ancient Egyptian samples, these scales are present but less pronounced as a result of degradation processes. Furthermore, the additional visible features are attributed to the dirt or soil remnants from the burial environment these objects are found in. Beyond morphological examinations and characterizations by SEM, energy dispersive X-ray spectroscopy can provide insight into dyes and mordants present in the samples. Mordants or binding agents were specifically of interest with EDS in the examination of these samples, as XRF analysis was unable to verify the presence and distribution of lighter elements of commonly used mordants such as aluminum-based salts. In EDS mapping, the uniform distribution of sulfur was consistent with the fiber identification of wool discussed previously, and the presence of aluminum relatively conformal across the mapped region, combined with hyperspectral imaging analysis identifying the dye present as matter, indicated an aluminum mordant was likely utilized in this sample.
1 minute, Madeline.
In contrast, additional EDS mapping of another Egyptian sample had less uniform aluminum distribution, but was still present across the entire fiber. However, when these aluminum maps were compared to those of silicon, the areas of intensity were in the same region and thus attributed to soil or burial debris on a sample surface, further validated by the identification of indigo via hyperspectral analysis, which does not use a mordant. Finally, degradation is not just an issue in ancient materials, but more modern materials as well. In collaboration with the Alberts Foundation, his series of works entitled Structural Constellations, consisting of geometric forms on plastic laminate materials, were investigated to better connect the materiality to the visual appearance of the artworks. Microscopic investigation revealed two distinct types of attributed feature morphologies, and FTIR spectroscopy revealed three distinct material groups across the 50 works. The first type of features observed are deliberate artistic choices, such as the sandblasted regions depicted in the micrographs here, as seen in the observed shading on the structural constellations on the previous slide. The second type is related more to the inherent differences in the unaltered laminate surfaces. Material group 1 has this smoother or more pristine surface commonly associated with formica or laminate materials. However, material group 3 has these fibril or void-like features across the surface. A comparison of FTIR with microscopy that found all works with this fibril or crazine-like phenomenon were melamine formaldehyde, in contrast with the smoother, more pristine surfaces in group 1 that were urea-based. Then, based on archival research at the Smithsonian, we were actually able to link these material trends with patents and advancements and urea plastic laminates that were specifically designed to address this sort of crazing phenomena and mitigate it in group 1. This has been sort of a brief overview and just kind of a quick blast of a lot of information related to the cultural heritage field, but I wanted to highlight and introduce this field that has not been always as discussed in different regions, and also just highlight here and acknowledge all of the collaborators we've worked with. It's a really interdisciplinary process, and it wouldn't be possible without these collaborations. And specifically, I would like to thank my fellow postdoc, Hortense Della Codra, who has worked with me on all of these projects and really been pivotal in advancing all of this work discussed here.
Great. Thanks so much for an excellent talk. I certainly have several questions I'll be posting in the chat, but if anybody else has questions, post those in the chat. And we will proceed with our final talk for this section, which is from Assistant Professor Paria Gharavi from University of Central Florida, who's going to talk to us about some of her group's work on ferroelectrics. So go ahead and share your screen and go ahead and get started.
Sure. Good afternoon, everyone. Can you hear me and can you see my slide?
Yeah, looks great.
Okay, great. Nice to see you all virtually. My name is Paria Gharavi. I'm an assistant professor in Department of Material Science and Engineering, University of Central Florida. My lab, Gharavi Electron Microscopy Lab, is focused on electron microscopy studies of novel materials. And before starting, I want to say that Happy Women's Day to everyone. And as a woman in science and as a soon-to-be mom, I'm so excited to be here and present a part of my research and here. So I really enjoyed all of the talks, and it seems that TEM has great applications in all different fields, including art, astronomy, physics, and for myself specifically, we can see the application of electron microscopy in electrical engineering. So today I'm going to talk about what is the origin of enhancing electrical breakdown strength that we can see in ferroelectric thin films. And in this presentation, I use 4D STEM technique. A quick background and introduction about myself. I got my PhD from University of New South Wales in beautiful Sydney, Australia. And then I moved to the USA to continue my research as a postdoc in Professor Eric Stack's group at UPenn. And then I got an offer in 2023 from UCF as a new faculty. From my master's degree, I can remember that I have worked very hard on electron microscopy, including SEM and TEM till now. The motivation of my research group in general is on structure, process, and property relationship at atomic scale. As you may all know that this is the famous pyramid in material science and engineering, that we have characterization at the center of this pyramid that make a connection between structure, processing, and application of materials. And using different characterization techniques, we can have a better understanding of behavior and potential application of materials. Also, we can develop new technology and new materials with different properties. So I work on very different and diverse projects. As you can see here, different thin films with different purposes. But among all of them, for today, I chose to talk about Alaskan ferroelectric memory, which is a new ferroelectric materials discovered in 2019. And I'm gonna start with a just quick definition of ferroelectricity for those who are not familiar with this concept. In electrical engineering and materials engineering, we have a category of materials which is called ferroelectric materials. They have a spontaneous polarization which can be switched whenever we apply an external electric field. And as you can see in this picture, the polarity of a ferroelectric thin film refers to the direction of this spontaneous electrical polarization that can be either up or down. And here, what is very important for us is that due to the little bit changing in the location of atoms, we have changing in the lattice parameters of our unit cell. And as a result, it's very important for us to have a technique to measure this strain. Here you can see whenever we have a thin film on top of the substrate, so because we have lattice mismatch, of course we have strain. It can be either compressive or tensile. And it's very important for us to measure this strain. In a very simple technique, we can measure this strain by measuring the distance between atomic planes using different softwares. And for example, one of them is called GPA, that we can have a reference area, as you can see here in the white box. And based on the reference that we have, we can measure the d-spacing and compare it to that one. And as a result, we can map the strain. And this is what we did for LNO thin films before, I think back in 2018. So we had LNO film on top of LAO film, which is a ferroelectric materials, and using GPA software, we could analyze and study the strain in two different directions. However, it's not very accurate. And if we are looking for a technique which is very accurate to give us the number, we should use other techniques like 4D stem. In this new ferroelectric materials, which is called Alaskan, whenever we have scandium doped into aluminum nitride thin films, we have ferroelectric properties. And as you can see here, in a simple way, we can measure the d-spacing from left to right, top to down. And what we can see is that the d-spacing of the film doesn't change when we move from left to right. However, we have a big change when we move to the bottom part of the film because of the lattice mismatch that we have in the system. And as a result, we can see more dislocation and defects whenever we get closer to the interface. However, we use 4D stem. And I'm happy that before me, some of the speakers talk about 4D stems, and it's a very hot technique in these days to use to measure and characterize materials in all the fields, from ferroelectric to semiconductors and energy materials. So using 4D STEM, we are able to get some information about the crystal structure, compositions, and strain distribution. And our purpose here is to measure this strain distribution. So as you can see, the same sample, the same film on the same substrate. So now using 4D STEM, we could measure the d spacing and the distance between atomic planes of the thin films with reference area that we have in a PT template and the bottom layer, so the reference area can be different. And what is very interesting to see a significant increase of out of plane, which is around 9%, and also significant increase of in-plane lattice parameter, which is around 5%. So this helps us to understand that it's very easy and very accurate to measure the strain using the 4D STEM. Now get back to the main design of the multi-layer that we have. So you can see that in these specific samples, we increased the number of interfaces intentionally. And with the same total thickness, we noticed that we have an increasement of the characteristic breakout field. And what's the reason? What's the origin behind of that is the propagation of the electrical tree being deflected by multi-layer interfaces, which is slowed by the relative compressive stress that we have in alternative layers. What does it mean? It means that by introducing more layers and more interfaces to the systems, we introduce the different amount of stress and strain to the system, which can slow down the electrical field. And what you can see here is the 4D STEM results that maybe in the TEM image, you can see that we cannot see the contrast between layers. However, in the 4D STEM mapping, we can see different colors, yellow, blue, and yellow, blue, which shows us the different strain that we have in our system.
Just 1 minute, please, Paria. Oh.
Everyone, and I'm happy to answer if you have any question.
Hi, everyone. I'm Louisa Mizash. I've been a member of the organizing team for the Women in Microscopy conference for the last 5 years. And as I've seen the attendee number grow every year, I feel prouder to be part of this community. So thank you all so much for being here. We'll kick it off right away with our first speaker. Alex Pipinos is a master's student in microbiology at the University of Delaware. Her talk title is Unveiling the Symbiosis, Visualizing Streptomyces cilicolor M145, a PGPR's interaction with Triticum aestivum. If you have any questions, you may put them in the chat during her talk, and we will get to them right afterwards. So Alex, the floor is yours.
Thank you, Louisa. So as I mentioned, I am a master's student in microbiology at the University of Delaware. I'm a part of the base lab, and I'll be finishing up this spring. So I'll be showing you a little bit about what I worked on the past 2 years or so. So I'm going to give a little introduction when the slide, there we go. Okay, so first I'm going to introduce what plant biostimulants are as an intro. So biostimulants are substances or living organisms that, when applied to plants, enhance nutrient efficiency, improve crop quality and traits, and increase tolerance to abiotic stresses. So that ultimately promotes overall plant health. And some substances that can function as biostimulants include seaweed extracts, amino acids, microbials. There are so many different types of biostimulants. But within plant biostimulants, there are also many soil inhabiting bacteria that can colonize the root rhizospheres. And the root rhizosphere is, let me add a little laser pointer, is this area of the soil that directly interacts with the roots, the plant roots in the soil. And that can facilitate some key biological processes. So some notable PGPR groups you may have heard of are proteobacteria, firmicutes, and actinobacteria. And in my presentation, I specifically focus on actinobacteria and more specifically the genus Streptomyces. And so overall, with the market projected to grow $7.6 billion by 2029, alongside an expanding global population, there is an evident need to continue advancing research and innovation in the biostimulants field. So I first want to introduce what Streptomyces are and a little bit about them. So Streptomyces are these filamentous gram-positive bacteria. As you can see in this image I took, they look a little bit more like fungi through imaging. So they have these three distinct developmental phases. The vegetative hyphae phase, which you can see in this image, there are hyphal extensions, and then aerial hyphae, which is oftentimes branching from the initial hyphae, and then lastly a sporulating phase. So they'll form these chains and then spread off and restart the life cycle. And Streptomyces are responsible for producing a lot of secondary metabolites and compounds with significant pharmacological and agrochemical applications. So they actually account for 70 to 80% of all known bioactive products. So overall, their metabolic diversity underscores the genus's critical role in both medicine and agriculture. And so our goal was to inoculate Streptomyces ceolicolor with spring wheat to analyze their colonization habits. Again, as I mentioned, this was just a part of my project. We wanted to one, look at their colonization habits, and then also examine whether Streptomyces was acting as an endophyte. So is Streptomyces entering the plant through some sort of mechanism? Okay. So we have a fixative and staining protocol that we developed. So we inoculated the bacteria onto the plant roots and let those sit for 3 different time points. And on those 3 time points, we harvested the roots, the shoots, and the internodes. The internodes are the root-shoot interface. And then we subjected them to a fixative protocol combined with vacuum filtration to remove excess particles that could interfere with the imaging efficiency, and would also allow for better penetration of the stains for the staining and fixative itself. And then once that process was complete, the samples were stained. So we stained them with calcifluor white, and that was for binding to the cell walls of the plants for imaging. And then the plants were immersed in wheat germ agglutinin 594, and that was for staining the cell surface glycoproteins to tag Streptomyces ceolicolor for fluorescent microscopy imaging. And I am trained on 2 microscopes. So I have experience with the Leica Stellaris and the Andor Dragonfly super resolution microscope, but all of the images that I'll be showing you in this presentation were taken using the Andor Dragonfly. Okay, there we go. I just want to mention, I'm sure a lot of people have heard of Z-stack analysis, but we used Z-stacking in our analyses because what it will do is take a series of images based on a defined Z-plane, and then it'll reconstruct everything to create one 3D image. And I used Amaris for my image processing. And so that was able to enhance the detailing of the plant and bacteria, and to also remove any background noise so that we can focus on the image itself. I have a video, but I don't think it's going to work. Let me try. If it doesn't work, that's fine. Okay. Well, I was going to show in the Z-stack video, you could see established colonization of bacteria and plant roots. So there it goes. So the Streptomyces ceolicolor are in red, and then they are colonizing these root hairs from the spring wheat roots in this cayenne color. Okay, so then we come to the images. So we determined that Streptomyces ceolicolor utilizes its hyphal extension properties in combination with plant root interactions to distribute itself throughout the 3 imaged root regions that we looked at. So we looked at the root tip, which is also known as the elongation zone, the middle root, and the upper root, which is also known as the maturation zone. And by day 5, after inoculation of bacteria onto roots, we found that Streptomyces ceolicolor colonization was evident across all 3 regions. And I've included representative images that I'll be showing from each region of the plant. So starting with the root tip region in figure A, we see Streptomyces ceolicolor with wrapping around the entire left side of the root tip, and then moving on to the middle roots. A surface analysis was conducted for the WGA channel, so that was the Streptomyces channel in Amaras. So that kind of allows to examine more the positioning of the Streptomyces ceolicolor around the root hairs. And you can see more hyphae tightly wrapping around the root hairs. And it's even evident that the Streptomyces are extending beyond that initial colony in the upper left section. And then next we have the maturation region, which is the upper root in image C. So this is a little bit more of a zoomed in image, but you can again see vegetative mycelia clasping to the mature root hairs of the plant. And then following the analyses of the root regions, we examined the root shoot interface. So this is also the internode. And this region exhibited the most extensive formation of vegetative hyphae with lots of colonization on these hair-like structures known as trichomes. So a possible explanation for this high level of colonization is that trichomes can serve as these microbial habitats, and a lot of bacteria are attracted to this region because there are potential openings for the bacteria to establish an endophytic relationship with the plant. And then lastly, we looked at the spring wheat shoots. So this was the leaf of the plant, and you see that there is colonization at this exposed region where I cut the plant for imaging. So either Streptomyces was endophytic at this point, and when we cut it, the colony was exposed, or the moisture in the in vitro environment that we grow our plants in could have caused the transfer of Streptomyces from the roots to the shoots via water or some other mechanism. And then just to get into our future directions. So the reason that we do all this, the reason we work with Streptomyces ceolicolor is because it's one of the few species of organisms that produce a antioxidant amino acid called ergothioneine. So plants and humans can't produce it, but as I mentioned, Streptomyces can, and it has been shown to be very beneficial to human health in some aspects. So it's very interesting in medical and agricultural contexts. So we've developed these quantum dots that can be used for specifically tagging ergothioneine. What quantum dots are these tiny semiconductor nanocrystals. So when you add the quantum dots to the inoculation, they can tag and visualize the protein's location and dynamics within a biological system. So we have quantified ergothioneine already, but it would be cool to visualize it in the biological system. So if you have any questions, feel free to ask, and thank you.
Thank you, Alex. Excellent talk. Any questions from the audience? Okay, I'll kick one off. I really liked the images you showed. Can you explain a little bit more how you captured those? I understand you did some Z stacking. I'm not personally familiar with that. So can you explain how those are reconstructed, what the microscopy technique is called?
Sure. So we use the super resolution microscope. So that's from the Andor dragonfly. I know the Leica stellaris is just a confocal microscope, and you can also do Z stacks with those. So what it'll do is I'll define one side of the Z plane and then move it towards another side of the Z plane. And then it'll take a series of thousands of images and then reconstruct it to create like a 3D image. So in this video, you can see it does look a little bit 3D. And the reason we wanted to do Z stacking was to see if there was a way that we could visualize the bacteria going into the plant, so acting as an endophyte. Initially, we were really looking for that with the Z stacks.
Thank you. We do have a question in the chat. Could you clarify what specific super resolution imaging modality you implemented using the Dragonfly? Is it a single molecule localization microscope? Is it SIM, structured illumination?
I think we just used the Z stacking aspect of the super resolution microscope, but I can check and get back to you on that.
Okay, thank you. Okay, another question. This will be the final one for the sake of time. The antioxidant compound is super interesting. Is there evidence that the organism is using it to deal with ROS? Is it a defense compound?
Yeah, so we have found that ergothioneine is a secondary metabolite from Streptomyces ceolicolor. So when Streptomyces are grown under more nutrient minimal conditions, it produces less ergothioneine. So that's something interesting. And we're doing a bunch more experiments to see specifically the biosynthetic pathway of prokaryotic ergothioneine biosynthesis. But it's certainly an interesting amino acid that's gaining more traction in research.
Thank you so much, Alex. If there are any other questions that come up in the chat, please try to answer them. We'll move on to our next speaker. Our next speaker is Amarasinghe. She's a PhD student at the University of Tennessee. And her talk title is The Role of Non-Equilibrium Ribosomal Dynamics in Facilitating Nucleoid Separation. Chat whenever you're ready.
Thank you, Louisa. So I'm Chathuddasie Amarasinghe, PhD student from University of Tennessee. And first of all, I would like to thank the organizers for giving me the opportunity to talk about my research on the role of non-equilibrium ribosomal dynamics in facilitating nucleotide separation in E. coli cells. So imagine E. coli cells or live E. coli cells is a little tricky because they grow and move around. In other similar studies, cells are often fixed to glass slides using different chemicals, and we have tested the effects of PLL, which is commonly used for this purpose. And we observed that PLL can affect normal cellular processes. For this study, we try to image cells non-invasively as possible, as this knowledge has potential applications in finding novel antibiotic targets and developing synthetic cells. Therefore, we use PDMS-based microfluidic technology to achieve this goal. Using E-beam and photolithography, we make patterns on silicon wafers, and these silicon wafers will then be used as molds for PDMS-based microfluidic devices. Our design consists of a larger main channel, shown in green in the design, that allows media flow, and then there are side channels on either side of the main channel where E. coli cells will reside during the experiment. The dimensions of the side channels are very important because if it's too tight, the cells won't grow normally, and if it's too large, they will move around. And then we image E. coli cells using our Nikon TI inverted fluorescence microscope. We also use a motorized stage that allows us to take time-lapse images of cells in a bunch of different positions on the microfluidic device. And this method allows us to image thousands of cells, providing us statistically robust results. So what exactly are we studying in E. coli? The chromosomal DNA in E. coli is phase separated from other cytosolic components into a region called the nucleide. And during the cell cycle, the nucleide will replicate, separate, and segregate into two daughter cells and undergo cell division. The potential mechanism for segregation is known to be entropic or the intrinsic entropy in the nucleide. And the surprising thing is once the two sister nucleides lose contact, these entropic forces vanish, but experiments show that nucleides continue to move in opposite directions at the same rate even once they lose contact from one another. So what mechanism actually drives nucleides apart and allows them to partition into daughter cells? In 2021, Meier et al. Proposed a reaction diffusion system that includes the formation of polyribosomes in the nucleide region. Polyribosomes exert excluded volume effects on the DNA. Therefore, according to equilibrium physics, polyribosomes or polysomes will be excluded from the nucleide region. However, this non-equilibrium model by Meier et al. Predicts that polyribosomes accumulate at mid-cell and lead to the formation of nucleoid lobes that will eventually drive them apart. So to test this model experimentally, we engineered an E. coli strain with RPS-BM cherry label to image ribosomes and Hape MBIPET label to image DNA. Using the signal from these species or fluorescent markers, we will capture them at a specific frame rate, and through different techniques, we can determine the spatial and temporal progression of these two species in the cell. Here on the right, I'm showing you the density of ribosomes and nucleides along the long axis of the cell from cell birth to cell division. And on the left, you can see the typical signal of each species at approximately this time point in the cell cycle. So what we see is that there is an accumulation of ribosomes. We can observe it at cell center. However, it is observed throughout the cell cycle, and it starts at the beginning of the cell cycle itself. And the nucleide separation occurs much later. And this is not consistent with the equilibrium model because this shows that ribosomes are not 100% excluded from the nucleide region. And due to the co-localization of ribosomes and nucleides at cell center, at least in early cell cycle, we can't say that ribosomes drive nucleides apart. For better comparison with experimental results, with the help of our collaborators, Dr. Maxim Laurentwich and his student Mohang Chan, we came up with our own reaction diffusion model consisting of DNA, polysomes, and ribosomal subunits. We determined spatiotemporal organization of these three species using fixed law of diffusion and reaction equations corresponding to central dogma processes in biology, such as transcription. Here I'm showing you the density or the spatial distribution of DNA in green and ribosomes in red along the long axis of the cell at different cell ages obtained from experimental results. I'm sorry. I think you can still see my screen. So,
Yes, it's good.
okay. So, so these are different time points in the cell cycle. And at point 3, you can see both ribosomes and nucleide signals kind of overlap with one another. So, yeah. And then I'm showing you, I guess you can still see my screen, right? I'm sorry, because my screen was kind of acting crazy.
Yes, we can still.
Okay, so the top row is from experimental results, and then in here I'm showing you the spatiotemporal organization of these two species from our reaction diffusion model. In case you're wondering why they look different from experimental results, it is because of the 1D nature of our model, and in reality, E. coli is a rod-shaped cell with hemispherical caps. We can artificially incorporate the geometry of the cell in our model, and the density of the two species will show close qualitative match to our experimental data. So both reaction diffusion model and experimental data shows a broad accumulation of ribosomes at mid-cell, and this is observed before minimum in the nuclear density appears. As cell cycle progress, we see more negative correlation between these two species. And to look at this more carefully and how to see how these densities evolve through time, in this plot, I'm looking at the density of the nucleide signal in a band of fixed width at cell center from cell birth to cell division. In the beginning of the cell cycle, the nucleide density stays pretty much constant and then drops due to the formation of a minimum in nucleide density at cell center. Simultaneously, the ribosomal density spikes up to fill up the space previously occupied by DNA material at mid-cell. And this region, where ribosomal signal goes up and the nuclear signal goes down, is consistent with the equilibrium model. However, in the early cell cycle, the period where both species prefer mid-cell is only consistent with the non-equilibrium model. As different periods in the cell cycle show varying dynamics between DNA and ribosomes, it is essential to test polysome-driven nucleide separation in different periods of the cell cycle separately. To further test polysome-driven nucleide separation, we stopped polysome production using rifampicin, which is an antibiotic. But first, we'll see how cells behave before the rifampicin treatment. To focus solely on polysome-driven nucleide separation, we removed effects of cell constriction by treating cells with cephalexin. In these cells, other cellular processes should be unaffected. And as cell cycle progress, ribosome intensity at mid-cell gets narrower and more intense. And corresponding to this high-intensity region, there is a low-intensity region at mid-cell in the nucleide signal chimograph. And then using rifampicin, we inhibit transcription, and as a result, polysomes dissociate into ribosomal subunits. And due to their small size, ribosomal subunits will be uniformly distributed throughout the cell. And in these cells, the minimum in nuclear density is not well defined as polysome production is turned off. So our data suggests that ribosomal dynamics facilitate separation of daughter chromosomes. However, it is not the only driving force, and there are other cellular processes such as cell constriction that can help with nucleide separation. And this marks the end of my talk, and I would like to thank everybody involved in my research and the funding sources. Thank you for your attention, and I'm happy to answer any questions you may have.
Thank you so much, Chat. That was an excellent talk. We do have one question in the chat. How is cell cycle stage determined in these studies? Are there chemical measures, or is it done with imaging from visual cues or just from timing?
Yeah, that's a great question. So after we get these images, we segment them using a central neural network. I'm trying to go back to the very first slide. And then we track the lineage of these cells, so we can determine when the cell is born and so this will the time where the cell divides or the cells will fully separate is it marks the cell division for the mother process or mother cell, and then it also marks the cell birth for the daughter cell. So that's we track it throughout the experiment, and we kind of make a very big data set with all this information.
Okay, thank you so much, Chat.
Thank you.
We will move on to our third speaker. Our third speaker today is Madison Ammon. She's a PhD student at The Ohio State University. And her talk title is Correlating Min-Flux Nanoscopy with Single Channel and Nanoscale Patch Clamp Reveals Unanticipated Cooperative Gating of Cardiac Sodium Channels. Madison, the floor is yours.
Hi, everyone. Today I'll be presenting recent work from my group where we were able to correlate structural min-flux data with functional patch clamp results in order to further investigate cardiac sodium channel interactions. Traditionally, when we like to think of cardiac conduction, we tend to think of it on the whole organ scale, specifically how signal propagates down the heart in order to allow it to contract and beat as one succinct unit. In order for this to be possible, though, there are a series of processes that have to happen on the cellular level. As shown on the left, two cardiac cells are both mechanically and electrically coupled together, and they're able to stimulate one another through a series of events known as the cardiac action potential. Throughout the cardiac action potentials, ions flow in and out of the cell, and the initiation of this process, where cells initially get electrically excited, happens through a rapid influx of sodium ions into the cardiac cell. These processes happen at the cellular endings, as that's where a large cluster of sodium channels localize, as shown in the figure on the right, and the sodium channels are the green molecules. It's important to note that the structural layout and localization of these sodium channels critically impact their function. Previous work from our group has shown that there are differences in sodium channel localization within healthy and diseased models. Therefore, it is important to understand the localization in a variety of settings. The main method our lab likes to use is microscopy. And as we all know, microscopy is a resolution game. We typically like to start off with doing confocal microscopy, where we're able to fluorescently tag and label various proteins within cardiac tissue, visualize and image them, and then we can make measurements based on their spatial association of one another. But because confocal microscopy is a diffraction-limited technique, we're still not able to answer all of the questions we have about specific sodium channel localization and the way they cluster. We can transition to use other higher resolution methods, such as TEM, but with TEM, we're not able to tag proteins and visualize those proteins that are tagged. Therefore, we're only able to look at cardiac ultrastructure with this method. We can also transition to using other super resolution microscopy methods such as STORM. STORM relies on stochastic blinking events of fluorophores in order to get sub-diffraction resolution. But with this technique, we're still only getting around 20 nanometers resolution, which is still not good enough to answer some of the critical questions we have about sodium channel clustering. Min-flux microscopy is a new super resolution light microscopy technique that's capable of achieving 1 nanometer resolution. The way this technique works is there is a donut ring excitation beam, as shown, with a central intensity minimum in the middle. This beam will circle around the fluorophore it's trying to localize, and it will try to align the central minimum of this beam with the fluorophore localization. This is how this technique is able to precisely localize fluorophores while collecting minimal photon emission. Because this is a relatively new technique, it hasn't been tested in a lot of biological systems, so we undertook the challenge of trying to image optically dense samples such as cardiac cells. As you can see in panels A and B, we have a typical confocal image where we are able to fluorescently tag sodium channels and visualize them. As you can see with this, we're able to confirm the presence of these proteins within the cardiac cells, but we're not able to get exact measurements about the sodium channel densities, and we don't really get to see what these clusters look like. And panel C is in a MinFlux image we were able to take where we were accurately able to tag sodium channels and image them with around 2.4 nanometer resolution. If we look at the zoomed in panels, we can see that we are able to see specific information about sodium channel clusters, their size, and sodium cluster density from this sample. Once we were able to validate that we were able to visualize these clusters with this technique, we then wanted to see if we could manipulate sodium channel clusters and quantify this manipulation with image analysis. Therefore, we treated the same cardiac cells with a drug SB2, which is known to enhance sodium channel trafficking. We tagged the sodium channels, imaged them, and then through an image analysis software I wrote, we were able to assess the cluster density and cluster sizes and confirm that SB2 was able to enhance sodium channel clusters and density. We then wanted to test this method in one of the disease models our lab is currently studying, delta KPQ. Delta KPQ is a mutation that is associated with arrhythmias in human patients. We therefore imaged cardiac cells that were harboring this mutation. We imaged cells that were untreated and cells that were treated once again with SB2 to enhance sodium channel trafficking. And through the same image analysis I previously talked about, we were able to confirm that the presence of SB2 was able to increase cluster density of sodium channels within this mutation. Now, we wanted to further understand the functional effects of increasing sodium channel clustering for this specific mutation. Therefore, our collaborators undertook a series of functional patch clamp studies to see these functional effects. Through the results, they were able to confirm that by increasing sodium channel clustering with SB2, we were able to decrease the presence of unwanted electrical activity that typically results in arrhythmia and reduce the arrhythmia potential of this mutation significantly. Now, we then wanted to see, okay, now that we were able to use this technique, validate that we can visualize sodium channel clusters, and we were able to test that drug SB2, we wanted to see the clinical effects by using it in an in vivo animal model. Therefore, we treated mice that have an arrhythmia mutation with this drug, and we were able to do ECGs and see that there was a significant reduction in the arrhythmia burden of the mice that received the SB2 treatment. Now, I would like to end my talk with kind of re-emphasizing the importance of understanding sodium channel clustering at the single molecule level and the importance of MinFlux. Previously, other microscopy methods have not allowed us to get the information that MinFlux provided us. We weren't able to make distinct measurements about sodium channel density measurements and about cluster sizes, and the capabilities of correlating this information with the functional results we received led to further insights of the importance between the structure and function relationship sodium channels have on whole heart electrophysiology. Now, this pipeline of starting here and moving all the way up to in vivo and clinical models spans beyond the scope of our lab and can be important to a wide variety of diseases and specific therapeutic drugs that want to be potentially tested. I'd now like to thank everyone that was involved in this project, and specifically our collaborators, Otto from Barrier, who helped us get the microscope and be able to start using it. And then here are all of our funding sources. And thank you all for listening to my talk. And now I'm open for questions.
Thank you, Madison. That was a beautiful talk. Are there any questions in the chat from the audience? Okay, Miranda, thank you. Are these channels mobile in the cardiac cell membrane? Are they free floating in the bilayer or anchored in any way? And would this affect what you see?
Yeah, that's a great question. So when we're imaging on fixed cells, but they are being trafficked to the membrane. It would be really interesting to see kind of what that trafficking looks like along the way, but they are anchored into the membrane once they're trafficked there. But again, because we're seeing fixed cells, we're just seeing that process as it's frozen.
Okay, our final speaker is Aikaterina Filopoulou. She's a PhD student at the FZJ Institute in Germany. And her talk title is Cryostem of Biological Macromolecules, Visualization by Integrated Differential Phase Contrast.
Thank you for the kind introduction. Hello to everyone. I hope you can see my screen. So today
Yeah, Aikaterina, we can't see your screen.
Perfect, thanks. So I'm a PhD student at Forschungszentrum Jülich in Germany in Carsten Zach's group. And today,
I'm sorry to interrupt. We cannot see your screen.
Ah, interesting. Let me share. Yeah, I guess now.
Okay, now we can.
Super.
Yes, perfect. Thank you.
And today I would like to talk about my project in cryostem for biological macromolecules. And more precisely, the approach that we use is the integrated differential phase contrast. As I will talk in a structural biologist audience, I would like to give a bit of the background regarding STEM. So in scanning transmission electron microscopy, we need to focus our beam into a certain spot to have our probe, and then we are scanning our specimen. And after that, we are able to capture the signal that is a result of the interaction of the probe and the specimen. The advantage of this method is that we can collect simultaneously different kind of signals in parallel. For example, the bright field signal, the annular dark field, etc. But an important parameter to form our probe and its geometry is the convergence semi-angle, the alpha that you can see here. So with that, we are able to fix the depth of focus, and also it's related with the maximal theoretical resolution that we can reach. As we are opening our convergence semi-angle, our probe, we are decreasing the depth of focus, and then we can reach higher resolutions. Here, in the differential phase contrast method, to be able to capture this kind of signal, we use at least a 4-quadrant segmented detector. In our case, the Panther detector. And with that, we are able to detect the displacement of the electric field. As the electric field is electrostatic, then we are able to integrate that and have the electrostatic potential field, which is representative of the material that we have. But what are the advantages of IDPC and why this approach? With IDPC, we are able to image heavy but also light elements at low electron doses, something really important for structural biology. Also,
please, everyone, keep yourselves muted. Thank you.
Also, there are no oscillations of the CTF, and then we have the most of the signal. And at the end, as the field is electrostatic, then the non-conservative noise which is produced is suppressed. And with that being said, I will jump directly to some of the results. So, here, in this experiment, we have used the tobacco mosaic virus as specimen. We know its structure, its helical structure, and in this case, the convergence semi-angle that was used was set at 2 millirad. The experiment has been performed on Titan cryos at 3000 kV, and the micrographs have been manually collected. And you can see the amount of micrographs that have been collected. The total electron dose was set to be identical to the typical dose for cryo-EM. And then before processing, we high-pass filtered the micrographs to avoid to get rid of some artifacts that are provoked from the nature of the detector. And here you can see a micrograph that is high-pass filtered. For processing, I have used the CryoSpark, and I have selected these 2D classes, and the total number of segments was approximately at 20,000. So at the end, I have proceeded with helical refinement, and the final resolution was at 5.3 angstrom. You can see that the model has really been good fitted in the map. And also from the 2D classes, you can see some really good 2D details of the structure. The same experiment has been done at 4 millirad. Again, the micrographs have been manually collected, and you can see some details in the 2D structures. And at the end, the final resolution was at 3.6 angstrom. Okay, I keep talking about resolutions, etc. We are still at near atomic resolutions, but not at atomic resolutions. But why you should keep these resolutions in mind? As mentioned previously, the opening of the probe, the convergent semiangle, defines the maximum theoretical resolution that can be reached. So you can see that at 2 millirad, the maximal theoretical resolution is at 4.9 angstrom, and at 4 millirad at 2.5. And with this small amount of particles, we have proven that we are able to reach near atomic resolutions, but also to be really close to the maximal theoretical resolution. Regarding dose fractionation, in cryo-EM, it's really common to collect frames and a stack of micrographs on the same area. Here we have performed the same experiment in STEM, and the electron dose of each frame is set at 40 electron per angstrom square. 3 frames have been captured, and you can see that as the electron dose is increasing from already the 80 electrons per angstrom square, the layer line, the high frequency layer line, is fading away. Although I still wanted to perform some 3D reconstructions, and as I had the movies, I high-pass filtered them. You can see that the contrast is really better than in the single micrographs. Then I have performed motion correction, and at the end, approximately 5,000 particles have been selected. And that led to a final resolution at 3.7 angstrom. The map looks good. You can see the alpha helices and some good details. It's still work in progress, but we already have the suspicion that as the contrast is better in movie series, it might help the already existing softwares to align better for the 3D refinements. And with that being said, I would like to thank you for listening to my talk. And also I would like to thank my supervisor, Karsten Zachse, our collaborators in Thermo Fisher, and also in the project of For the biostem from the University of LMU and EPFL. And with that being said, I'm open to your questions.
Thank you very much, Aikaterina. That was a wonderful talk. One very brief question. For the cryo work, do you have a problem with preferential orientation for such long and one-dimensional structures?
No, I have not this problem regarding the orientation, and you can see, of course, there is a preferred orientation, but it's something that is also based on the ice thickness. But at the end, it's not something consistent. You can see different orientation in different movies, so yes.
Welcome to today's panel on data management and visualization. I'm AJ, I'll be your moderator. We are thrilled to have you all here for what promises to be an insightful discussion with our expert panel. Before we dive in, just a quick note on logistics. If you have any questions, feel free to just drop them in the chat and I'll address them during Q&A. And now let me introduce you our distinguished speaker, Dr. Tobin Magle, lead data management specialist at Northwestern University with extensive experience in research, data management, and open science practices. Toby, please just go ahead and share your screen whenever you are ready.
So yeah, I'm currently at Northwestern University. I'm the lead data management specialist in research computing and data services, which is a unit in central IT that helps researchers use technology. And Colby is also in that group with me, and she's going to tell you about visualization later. But I've also done a lot of work at other universities throughout my career, essentially focusing on teaching researchers how to take care of their research data. So I'm going to talk hopefully briefly about improving your data management skills. And if I start going much over 10 minutes, just start waving at me because I get carried away sometimes. And I want to make sure that everyone gets their full time to talk and you get to answer questions. And I did put a link to these slides in the chat because on the last slide, there's a self-assessment that I'll leave you with at the end of the talk. All right, so today we're going to talk briefly about the consequences of what not managing your data. Then we're going to talk about the good data management practices and then show you the self-assessment. So I know that when I was doing my PhD in microbiology at the University of Wisconsin-Madison, one of the first things that I asked my PhD advisor when I started my own project was like, where do I put the data? Like, are there any structures? Like, what's the organizational scheme for this lab? And I guess I should have known then that I was a big data nerd. But she basically just said, do what works for you. And I was like, okay. So that said to me that data management was not something that was going to be valued in that research group. And I didn't spend a whole lot of time on it. So my data ended up everywhere. It was on my personal laptop, it was in Google Drive, it was on thumb drives. It was basically anywhere that you can think of to put data. And when I left that lab, I put all of my research data on a CD-ROM and it got put in a drawer somewhere. That probably dates me pretty well, but yeah, so I think the default assumption in a lot of labs is that research data management isn't something that people should be spending a whole lot of time on. But if you don't think about it ahead of time, you get data that's stored everywhere, you don't have any documentation, and there's no quality controls, and you don't know what the most recent version of anything is. So that begs the question, like, if you actually need to go back to your data later, if you put your project down for a few months, like let's say you submit a paper and have to go back to revise a figure, can you find what you need? Are you going to be able to use it? And I'd say for the most part, people can get over those hurdles and make it so that you can use your old data, even if you haven't really put a lot of time into managing it. But it's going to be really hard. You're going to spend hours of wasted time that you could have saved yourself if you would have thought about this stuff up front. So now onto the good data management practices section. There's too much stuff in here to talk about in 10 minutes. So this is basically going to be the data management fire hose. A lot of it's going to be surface level stuff I'm just going to shoot at you. And I'm going to try to dive in a couple of places that I thought might be more or less relevant to microscopy. So major sections, first off that you want to do is make a plan. If you've thought at all at the beginning of your project about how you're going to manage your data, you're probably ahead of most people. Even when PIs write a grant and they write a data management plan, usually it's like checking a box essentially. They write something just so that they can submit the grant and they don't put a lot of thought into it and they never look at it again. But since they're often required by funders, they're all kind of responding to the same federal mandate. There's certain things that you have to put in it, like what type of data are you going to produce? How are you going to document it so that you and other people can understand it later? How are you going to keep it safe? Where are you going to store it? And who's going to access it? And how are they going to get access to it? And that is during your project when you're working with your colleagues, and then after your project if you're going to share it with other researchers along with your publications. As part of this plan, you should be thinking about choosing your data storage. I know when I was doing my work, the data kind of landed where it landed. There was a lot of frantically going through poorly named files on my desktop to try to find what I needed. But as you're making your plan, you should ask yourself, do I have enough capacity to store my data? Data is a lot bigger now than it was when I was doing my work. I didn't really have to worry about it extending beyond my laptop, but now I'm dealing with researchers who have petabytes of data. And even our, campus scale storage system is running a little bit low on storage. You'll also need to think about whether or not it fits with your workflow. So I'm assuming that most of you are dealing with a lot of data that comes off of a scientific instrument. It probably lands on a computer that's next to the instrument, but where does it go from there? Where are you going to analyze it? Where are you going to store a stable copy of it? Things like that. And also, where is it going to go at the end of your project? Because at the point, let's go back to the capacity slide for a second. So capacity was never really a bottleneck before, but now that Google and companies like that are sort of clamping down the storage for higher ed, we're seeing a real strain on the system. So you have to think about, does it fit, and can I actually keep my data in the same place all the time, or do I have to move it to secondary or cheaper storage later when I don't have to access it as often? You also have to think about reliability. So you have a primary copy of your data stored somewhere, but you probably want a secondary copy somewhere else, and making the second copy is called replication. And even when you're working stuff in place, everybody makes mistakes. So it's good to use a system that has some sort of version control associated with it so that if you make a mistake, you can hit the back button and get back to where you want to be. And also, you need to think about security. There's lots of different types of technical controls that systems can have or systems don't have, like antivirus scans, encryption, firewall use, password protection, multi-factor authentication. And you don't have to make sure that your storage has all of these all of the time, but it's good to be aware of when you're missing one of these version control or replication so that you can supplement your data storage strategy with something that makes it a little bit safer. And even if you don't have something like encryption, that might not be a big deal for your data. Maybe your data doesn't need that level of protection, but just know when you pick a storage system, you should think about all these things and know what's missing so you know what kind of risks you're taking with your data. And after you've picked a place to put your data, you want to make sure that you're intentional about how to organize the data. I could stop this section right now just by telling you the advice of be consistent. And that's not only within one project, but with all your projects, because it'll help you find stuff later if you use the same strategy for all of your projects. And it also saves you time for coming up with a new strategy for every project. So find something that works for you, as my advisor said, but also be consistent with your work and with your lab mates' work optimally. One thing that I see as super useful is if you have a project that has sort of a limited scope, store it all in one folder so that it's portable. So if you need to back it up somewhere, or your computer dies and your computer is dying and you need to move it off of there, you can just grab the folder. Everything that you need is there and you don't have to worry about it. File naming is something that has really come to bite me when I didn't think about it. I would just, use the default file name when I was saving a file. It would be file 1, file 2, file 3. then I would have to open up each file and look at the rows and columns to try to figure out what the heck was in that file. So it's really good to kind of pick a few attributes about whatever data file you're producing. Sometimes it's date, type of experiment, sample name, and then order them in your file name from most general to most specific so that you can actually use the sort function in your computer to make things sort in an order that's useful. So one example is date. I have year, month, and day. So if I sort it in my file browser on my computer, it's sorted in chronological order. And the other thing for getting organized, last thing, is document everything. If you're working on a project actively, you can rely on yourself pretty well to mostly remember what's where. But if you have to put your project down for any period of time, you're going to forget things, no matter how important it seems in the moment, and how much you think you're never going to forget it. Write it down. So things like, what experimental methods did you use to create a sample? Where did the sample come from if you got it from someone else's experiment? If you run the sample on a microscope, like what was the instrument name, just in case there's something wrong with the instrument and you need to identify samples that you might need to rerun. And then after you have the data, like what type of analysis are you going to do with it? And also, if you're working in a group of people on the same project, who did what when, so that you can backtrack if something goes wrong. Now we're going to talk about collaboration. So how are you going to work with all of your colleagues during the project? Storage and organization has a lot to do with collaboration, making collaboration easier anyway. People are very good at hitting the share button, and it's files stay where they are, you hit the share button, people have access, but then you have a bunch of shared links that you have to keep track of. So my advice to you would be to store your data in a place where everybody who's working on that project has access. So store it in a central location. Northwestern uses SharePoint libraries for this purpose. And then make sure that you're only giving access to people who need it, and check who has access periodically to keep your data safe. And it also helps that if you're working together on a project, that everybody agrees on an organizational standard and how you're going to work together on it so that you can understand each other's data if one of you wins the lottery and never comes back to work again. And then finally, we have sharing. And this is mostly important because federal funding agencies require it. I know everything coming out of the federal government is a little topsy-turvy right now, so we'll keep an eye on this. But they essentially want you to make your data fair. And that stands for findable, accessible, interoperable, and reusable. So making it so that when you do share your data, other people have a chance of locating it and actually being able to use it for their own individual research. And one great way to do that is to store your data in a repository. I know every paper that I wrote in grad school, my advisor said, oh, just say you'll share it upon request. And that's really no longer sufficient. There's repositories that are open repositories that anyone can access. There's also controlled access repositories if your data has some sort of privacy concern. But in general, these mandates want the data to be as open as possible and as close as necessary. And if you want more details about what types of things people or the federal government thinks are good categories to have as a repository, there's this link in here that describes the desirable characteristics of research data repositories. All right, so that was the data management fire hose. This is the self-assessment. I'm not going to go through it, but it goes through each of the categories that I went through in the slide, and then the columns are different stages that you can be at in your development. And I would say that no one gets everything to optimal. It's okay if you have some things that are a little bit farther down the scale, but what I would recommend doing with this is identify where you are and pick one or two of these categories that you can improve on in the next few months, just to level up your data management and not try to reach perfection, but just to strive for some improvement. And that's all I've got.
Thanks, Tobin, for that insightful presentation on data management. So what I'm wondering is, how can microscopists balance the need for detailed record keeping with the fast pace of the scientific work, ensuring that they don't fall behind on documentation?
Yeah, I would recommend doing the documentation as soon as you can relative to the data collection. I definitely was guilty of waiting to waiting for a Friday when I had lots of time to do all of my documentation for the week. And it was miserable because I had to look up a lot more things. I was spending a lot more time on my documentation, even though it seemed more efficient to do it all at once. So doing it soon, and also think about, before you start collecting your data, think about what you need to collect, because that's really important. I've also worked with research groups who are trying to submit their data to a repository, and they're spending hours and hours and hours looking up data that, or metadata that the repository wants about their data. And it's just not available anymore, or they didn't collect it. So, yeah.
Thank you. So next we will hear from Dr. Sai, who is an associate professor in the Department of Biomedical Engineering at Ohio State University, and his research focuses on cardiac bioengineering. Sai, the floor is yours whenever you're ready.
Thank you, and thank you all for being here on a Friday afternoon instead of being out and about having fun. Hopefully this is somewhat enjoyable and useful. My obsession, I'm an engineer by training, right? So I don't believe anything has happened until I've seen it a few thousand times. So that carries through into my approach to data analysis, and I hope to convince you to be doing the same in your corners of science and why it's useful. I will present a couple of specific cases to illustrate a couple of broad points, right? I'll start with this very broad quote that I absolutely love from the English naturalist J.A. Baker, that the hardest thing of all to see is what is really there, right? Our senses are terribly limited, which is why we use microscopes and other pieces of hardware to translate reality that we can't access into forms that we can access. But sometimes that means the image from the microscope is not necessarily something I should be eyeballing to make an assessment. This is what mathematics is really for, right? So microscopes are particularly excellent at answering where type research questions. You ask it where something is, it's fantastic at doing that. In life science, light microscopy is heavily used, and the most common paradigm that you'll see for answering where type questions is something called colocalization or overlap analysis. These are really old traditional methods that are reliant on superposition of signals. But of course, we know that no two molecules are sitting in the same spot. So superposition of signals is really a function of poor resolution. And as our microscopes get better, these methods start to kind of let us down in places where we want to be careful about. There are other methods. If you're in continuous space where your space is not broken up into pixels or voxels, you can do things like cluster analyses, which we'll talk about briefly in a bit. But there's an underused, I'm going to turn off my slide timings. Bear with me just 1 second. All right, rock and roll. We're back on. All right, so point pattern analysis is a really powerful paradigm from spatial statistics that is criminally underused by microscopists. I'll tell you a little bit about that and why you might want to play with it. So the first principle is measure thoughtfully and measure a lot. Simply measuring a lot doesn't always get you the best answers. Here's an example of a problem that a biologist collaborator came to us with. These are pictures from light microscopes of cardiac muscle cells or heart muscle cells. These are big brick-shaped things with 2 nuclei because they're so big. And each one of these little red or green dots in these cells is a single RNA molecule that they've lit up using a form of in situ hybridization. The question they had was, the red RNA, which is for a protein called RYR2, never mind what it is, versus the green one for COM1, are they showing different distributions in space relative to the 2 nuclei, which are the little gray blobs in the cell? They looked at a whole bunch of cells, a few hundred in fact, using the traditional form of cross-correlation between colors. So in this case, they're cross-correlating red with gray or green with gray, and they're ending up with the result that, yeah, no, both of these really have the same sort of distribution relative to the nuclei. But there's one small little detail to be careful of. If you're looking for superposition, you're really looking at a tiny, tiny subset of the red and green signals. You're ignoring most of it, which is really the interesting bit. So we instead opted for a point pattern analysis-based paradigm, where we segmented these signals, measured their distances to the nearest nuclear pixel, and then looked at the cumulative distribution function of those distances, comparing the observed distribution against what we would predict if the signals were completely randomized in space. And of course, all this analysis is done in 3D because that's what our data is, but I'll show you everything in 2D for ease of visualization. And when we take the observed and the random distributions, we literally take a point-by-point difference of those and plot that. That's the bottom right panel in number 6, which gives us a very useful curve because essentially if the observed graph is left shifted from randomness, it means you are seeing shorter distances than you would expect under randomness, meaning you're seeing attraction. And if it's right shifted, it is the opposite. You're seeing longer distances. It is repulsion between these two components of signal. So we did this with their RNA data. We segmented them. We used exact Euclidean distance transformations to efficiently calculate these distances, both for observed and random cases. And when we plot those, first thing you see is the red curve is right shifted from my dotted black line versus the green curve is left shifted. And when we look at the difference curves, they have opposite polarity, meaning green RNA are attracted to the nuclei versus the red RNA are kind of repulsed by the nuclei. What this really means in biological terms is the RNA in red is being trafficked much more efficiently away from the nuclei than the green. And we would have missed all of this beautiful difference in the biology if we just driven by a smaller subset of information using old school analyses. So this is the discrete case. Now, what if we're operating in continuous space? You don't have pixels or voxels. You're just going to have point coordinates in some volume. This is common case with localization microscopy, storm, palm, minflux, etc. And so what do we do about this? And here the point I want to make is no matter how good your methods are, always be thinking about, is there a better way to do something, right? Typically in continuous space, you don't want to process a single localization because if you measure distances between adjacent localizations, well, the same fluorophore molecule gets localized over and over again. It's been undergoing Brownian motion between those events. All you will recapitulate is that your fluorophores are undergoing Brownian motion, which is a powerful illumination of the obvious, which is not useful. So instead, you use various forms of unsupervised clustering. Typically, one of the things we want is we don't want to have to know a whole lot about the system before we start analysis. So something like k-means is less useful because you need to know a priori the number of clusters you're looking for, and we won't know that with any kind of microscope image. So methods like dbScan, which is a density-based clustering algorithm, become extremely useful. This is work I did as a postdoc where we built a density-based clustering approach which finds clusters of these single molecule localizations from storm data. Once we have these clusters, we can fit convex hulls around the clusters, and then we can play all kinds of games of looking at how often do these hulls overlap, what is their distance distribution, etc. I was perfectly happy with this method for a while, but, there are always things that are in the margins poking at us, right? One of the problems with this method, well, it takes a long time to compute. It has what's called a second order time complexity, meaning if you double your data size, it will quadruple the runtime. And it requires a couple of user-defined hyperparameters, which either you want to pull out of thin air and hope to get lucky, which really doesn't sound scientific to me, so I don't do that. Instead, if I want to do this rigorously, I can use statistical methods like bootstrapping, but that raises the time complexity now to fourth order, which is going to eat a ton of time. For a single paper, we generated a few thousand images. It took about 11.5 months for us to analyze that data set in 2023, which got us thoroughly irritated thinking we don't want to wait that long after an experiment or a series of experiments to know what happened. The other problem with this algorithm, it only gives you information on a narrow range of length scales based on the parameter value that you put in. So for all this, we thought, okay, what if we could build a better algorithm that is computationally more efficient, doesn't need any user-defined parameters, and will give us information in one pass on all the length scales present in the data. Took a bit of thinking, but then my postdoc Andy came up with a really clever idea. He used Voronoi tessellation, which is a mouthful for saying something very simple. We're going to take the space around all these points, and we're going to chunk it up by drawing lines in such a way that each cell in this image now contains the chunk of space that is closest to the one dot that is also contained in that cell. In other words, the size of these cells is an inverse metric of how densely these points are packed together, right? If points are densely packed, they each claim a very small cell. If points are in loose, empty space, those points get to claim big, wide open cells. So we can then plot the distribution of in 2D area or in 3D volume or even in higher dimensions, the size of these tessellation cells and get a sense for instantaneous density of these points at each location. But then the question is, at what density do we consider this to be true non-random clustering? If you just drop a bunch of coins on the floor, some of them will end up next to each other. Doesn't mean they're attracted or there's some kind of process happening. That's just random chance. We want to be able to measure and exclude that. So traditionally, the way to do that would be you randomize your points, repeat this process a whole bunch of times, burn a bunch of computer time, and then eventually get to this random distribution. We thought about it for a little while and figured, well, if you randomly throw points into 3D space, the nearest neighbor distances form a Poisson distribution, which means the tessellation cell volumes should also follow an a priori knowable distribution. Turned out to be the case, turned out to be a type of gamma distribution. And instead of doing all this painful Monte Carlo stuff, one equation, solve it in a fraction of a millisecond on your computer, you get the dotted line, now you know what's non-random clustering. And the whole point of doing all this is so we can turn this unsolved problem into a previously solved problem. This is another principle that I deeply believe in. We took all this continuous space data, generated density maps and cluster maps using tessellation, and once we're there, we can easily discretize those without loss of information, turn it into pixels or voxels, and then put it into that pipeline we previously built. Why would I do something new if I already have a good tool for that? So, and another point here is when we're measuring these attraction-repulsion relationships, that parameter is bounded between -1 for perfect attraction, 0 for indifference, +1 for perfect attraction, -1 for repulsion, I should have said, which means any system that you analyze using this, the results are going to stay within a -1 to 1 Cartesian coordinate system, which is a very easy thing for anybody from any discipline to understand. It's a very easy quantitative way to track complicated changes. And
you have 2 minutes left.
Oh, thank you. And this method is more accurate across a wide range of data conditions. It's infinitely more efficient than previous methods. And it turns out it also segments all kinds of shapes really well. In this case, it grabbed the fibers pretty well. Not so much the nuclear pore complexes. I won't bore you with details, but with some minor modifications, we were able to do that as well, even measure the sizes of these structures, and they agreed with canonical methods. I will just say we weren't trying to build a segmentation tool. It accidentally worked out that it also does that. So be attentive to accidental benefits from what you're building. With that, I want to thank all the folks who did all the work. I just show up and take credit. Andy really built all the algorithms I showed you today. And the discrete space version of it is already published. So I'll stop here and take any questions. If you want to go grab the source code, it's on that link with the paper.
Thank you, Said. That was a fantastic overview. So now let's turn to Colby, who is a manager of data science and visualization at Northwestern University. Colby, please go ahead and share your screen.
Hey everyone, my name is Colby Witherup Wood. Thank you for the introduction. I also just want to say thank you so much for having me. I'm so happy to be here and to have been invited. And I look forward to there being a 6th annual Women in Microscopy conference. And excited to be here. I'm last. I think I'm the last one of the day, of the whole day. So taking it a little bit more fun here. Sorry, those were really fun. I didn't mean that. More relaxed than maybe I would normally do is what I meant. I'm going to talk about data visualization and presentation. And these are quite similar. They're very connected. Visualizations are things that are limited by space, and presentations are things that are limited by time. So there's actually a lot of overlap here between the two. And I only get, 10 to 12 minutes. I'm going to do my top 3 tips. I want to start talking just about conference presentations in general. Something that I've noticed over the years is that some people who maybe are like me, we show up to present at a conference and we're dressed very professionally, and we have practiced our talk 100 times. We have gotten the timing down to the second. We may talk a little fast because we packed it full of as much information as we possibly can. And then and one of the reasons we do this is because sometimes it feels like just for our results to be taken seriously or to be worth it, we have to first prove that we are smart enough, that we know enough for somebody to even listen to us. You may have other people I've seen in conferences, they show up, they're in shorts, and they stand up there and they get to slide number 4 and they say, I don't even remember why I put this slide in here, and everyone laughs. Or then they get to slide 5 and they say, oh, this reminds me of something else. I'm just going to tell you this story real quick. And they go off on a tangent. And then when it gets down and the person's waving the paper to tell them that their time is almost up, they say, no, I'm just getting to the good part. And then they go over time and everyone laughs. And I am not here to give you permission to not practice or to act unprofessionally for your talks, but something I want to say. So I just want to remind you all that you are so smart. I mean, you do microscopy, right? You're so qualified. Your technical skills are so impressive. I know a lot of times you can feel like, no, there's still 100 things I need to learn technically before I can get to that next level or before I can even compete at that next level. But I'm telling you, your skills are already very impressive. You also have a lot of professional skills. These are things people sometimes call soft skills. They're simply professional skills. These are going to be way more valuable to you than you know. You also know your data better than anyone else in the entire world. You've been with it for years. So what does this have to do with visualizations and presentations? I am giving you permission. You do not have to pack everything you know into one visualization or one presentation. This is my number 1 tip. You should use visualizations and presentations to highlight findings that are especially convincing of the findings that you have, right, of your argument, impactful in your field, or surprising. So maybe not what you expected or not what other researchers have found. So that's my number 1 tip. My second tip, I'm calling the ELSA rule. This is where you have spent 2 weeks creating the coolest chord diagram ever. You've been using color to indicate one thing and size to indicate something else and grouping to indicate something else about your data. You spent a long time working on this, and then everyone at your practice talk said that it was confusing. And maybe they give you some tips of ways to improve it, but you just have to let it go. It's not going to work, okay? And you have to let it go, and that's really hard. It's really hard for me. I love to make cool visualizations, but sometimes they just don't work. The same goes for, this other example. You did 3 years of bench work, and you ended up finding your results in publicly available data. And now you want to include 3 slides detailing your lab process in your presentation, because otherwise, what was the point? You just have to let it go. It's very hard, but that's my rule number 2, or my tip number 2. If you do like to make large and complex visualizations, those are best served in print or on the web. So somewhere where people can take time to actually explore that type of visualization. And they should be taking the time with it because they're interested in it. They're excited about it. They're exploring it. They're seeing where their model fits into this. Not because they're taking time to figuring it out because it's confusing. And I had to follow my own advice of the let it go when I was making this presentation, because I talk a lot to researchers across the university, and we tend to kind of generalize in a lot of these talks about, line graphs or bar charts and that types of thing and giving best practices. But I looked at the Journal of Microscopy, and there's a lot of images. There's a lot of illustrations, really cool illustrations, a lot of really cool like schematic diagrams and things like that. And so I'm not going to, talk to you about line charts and bar plots because I don't think it was as applicable. So my third tip, I'm switching to another Disney movie here because it was a pattern. Ask for feedback early and often. And this is something I never learned until I got into outside of the academic pipeline. Remember, you are not the target audience for your presentation. You know it all already. Your advisor is also not the target audience. They know it all already, right? But I do acknowledge that sometimes your advisor is the target audience for your presentation. So, and I don't mean that by saying, the target audience are people like your advisor, like other faculty members in that field. What I mean is sometimes doing things your advisor's way is going to serve you better in that moment, and serve your career better in that moment, than making a more general presentation or something that's going to appeal to more people that are actually there. So I do acknowledge that as well. But if you are trying to appeal to your audience, you're going to ask for feedback. When your presentation gets accepted or announced, the very first thing that you should do is put feedback sessions on your calendar between the day you find out and the day of the presentation. You do this because this is also creating deadlines for you. It's a deadline to have something down for the first, feedback session, and then to have it a little more polished and a little bit more. So it's helping you, but it's also going to help you make your presentation better from the feedback. You can invite co-authors of any of the papers that you may eventually be publishing with this. They should be invested in this as well. Grad students are great, whether you are an undergrad or a postdoc. Grad students, they like to do this. They're great people to ask. If you're in a journal club, you could ask for time at a journal club, or you could ask people to stick around after a journal club meeting. That's a great way to get people for feedback. You can always bring snacks or something that they like. Other presenters, you could always do like a quid pro quo. I heard you're presenting at a conference coming up. Can we do a feedback session where we each give each other feedback? If you're at Northwestern, we have a program called BYOD. These are working groups that meet together around particular topics. So feel free to email me and ask me about those. It is okay to get feedback at a very early stage. That's something I think that most of us are scared of, but that is good before you spend the 2 weeks on the diagram. You should schedule feedback sessions for at least twice the length of the presentation. This is something people forget. They invite you to their 30-minute talk. They schedule 30 minutes, right? And there's no time to get the feedback. And then make sure you have some of these sessions that are one-on-one, because there's a lot of groupthink that happens in those group sessions, right? Feedback sessions. The first person to speak, the loudest person to speak, tends to define what the rest of the feedback is going to be about. And that's not how people take presentations in usually, right? You're sitting alone in a quiet room while you're listening to the person speak. And so you really want to kind of recreate that and get the different perspectives. But, and then for visualizations, definitely you can send these and give people time with them, because that's how they will process a visualization in a paper, for example. You should ask them a list of short questions, but it should always have this one question, which is, what did you get out of it, right? You don't want to just say, can you tell me ways to improve it? The best way to know if you did a good job is if your point got across. So what was the point? What did you learn from my visualization? To see if it matches up. And my last tip here about feedback sessions is be prepared for conflicting feedback, right? And when you're deciding who to listen to, you should consider the reviewer's previous knowledge of the subject and of your work, and think about who kind of matches closer to your audience, either at a presentation or the journal that you're submitting to, right? Is it a more general journal? Is it a very specific journal? And so keep that in mind with conflicting feedback. And that is all I have. My top 3 tips: simplify, cut, and listen to the feedback from others.
Thank you, Colby. So what I'm wondering is, when designing figures, what are the best practices for choosing colors that remain like clear and distinguishable on different screens?
Yeah. So there are websites that you can go to for this that will show you different things. And I think that there's there's a lot of people who, for example, aren't colorblind, and they say, oh, you have red and green. People who are colorblind can't see that. But if you're not colorblind, you actually don't know what people who are colorblind, what shade of red and which shade of green. This is very strange, but I happen to have brown-green color blindness myself. And so it's not like I can't see every shade of brown or every shade of green, right? And so there are websites that actually recreate this for you. And so if that's your concern, and also for different screens, the other thing I would do is, I'm big on modeling. So if you saw a presentation where you thought the colors looked really nice, right? Make note of that, right? Make note of it. It's okay to be inspired by other people's work rather than just starting from scratch.
Mm-hmm. Yeah, thank you. So we still have like 3 minutes left. If you have any questions, feel free to just drop them in the chat. And that wraps our panel. And let's thank our speakers one more time, Tobin, Sayee, Colby. Thanks for sharing your expertise today, and we truly appreciate your time.
Welcome back. And thank you. Thank you all for attending today's conference. We hope that you had a wonderful time. I know I did. We want to take a second to thank our speakers and our panelists, and especially our keynote, Dr. Michelle Thompson, for sharing their research, stories, and perspectives. We also want to thank our planning committee, including Katie, Marie, Daniela, Liz, Thomas, Andreas, Patty, Louisa, Aubrey, Kana, and Ejay, without whom this would not be possible. And also this year we had incredible IT support from Isa. Thank you, Isa, so much. It went so much smoother with your assistance, so thank you. Lastly, we want to thank our incredible sponsors, the Northwestern MRSEC, JEOL, Hitachi High Technology, and Oxford Instruments. Thank you again, and we hope we see you all again next year.